of Patras, the European Mediterranean Center for Climate Change, the region of Puglia, which is the leader of the project, and the European Group of Territorial Cooperation of Xenopoli, and of course the region of Western Greece. So for the beginning, I would like to welcome the governor of the region of Western Greece, Mr. Nektarios Farmakis. So, Mr. Farmakis, please, you have the word.
Good morning, everyone. Welcome in TRITON's final event, which was planned at first to give us the opportunity to meet physically each other and exchange experiences from the project's implementation and results. Though COVID-19 unfortunately forced us all to adapt our planned actions and events according to the latest instructions for public health. So, we have chosen to organize TRITON's final event as a web-hosted event because our primary interest is to protect the health and safety of the participants and their families, friends, and of the greater community. We hope this global pandemic will fade soon, giving us the opportunity to meet with you physically in the near future. Before proceeding, I would like to call you a whole minute of silence in the memory of the victims of COVID-19. Dear friends, once again, I'm delighted to welcome you all to the TRITON's final event, and I want to thank the scientists who will speak here today for all the work they've done to advance our knowledge regarding the coastal erosion that our regions, the region of Apulia and the region of Western Greece, face. Furthermore, I would like to extend a special welcome to Mrs. Ranieri, Project Officer of the Joint Secretariat of Interreg 2014-2020 program, for her cooperation and support for the great job done. The sustainable management of coastal areas, or in other words, the combination of coastal land exploitation and the protection of conservation of habitats and ecosystems, is a strategic issue for our regions and for our countries in the path towards an alternative blue growth economy, in accordance with European strategy. Naturally, a key factor of the success towards this goal for blue economy is the existence of strong political commitment between the countries and regions involved to negotiating, cooperating, and developing new synergies, strategies, and actions. Therefore, we welcome the Maritime Borders Agreement, delimiting an exclusive economic zone between our two countries, inked this June by the Greek Foreign Minister Nikos Dendias and his Italian counterpart Luigi Di Maio, and we hope for further cooperation in the future. This demarcation case between the two countries was pending for more than 40 years, since 1977. For Greece and Italy, for Western Greece and Apulia, addressing the problem of coastal erosion is a key priority, considering not only the invaluable environment of their coastal ecosystems, but also the importance of the coastal zones in their economy. However, to tackle this problem, we need to build a common understanding regarding environmental protection, nature and biodiversity management, ecosystem services, and climate change adaptation. This prerequisite is recognized by the region of Apulia and the region of Western Greece, since we are both highly sensitive to coastal planning-related issues because of our special characteristics in terms of the natural coastal environment and the resources we have. Indeed, our regions are focused on protecting those sensitive areas, taking advantage of the scientific progress, new technology achievements, and the exploitation of the available European programs like the Interreg Greece-Italy program, in order, of course, to make a step towards an integrated coastal zone management. These are the reasons that gave birth to the TRITON project, named after a sea deity from the Greek mythology, son of Poseidon and Amphitrite. Triton was thought to live in those seabed, in his parents' golden palaces, and often taking the form of coastal wave, used to grab herds of animals approaching the shores. To protect his property from Triton, a shepherd from Tanagra cut off Triton's neck while he was asleep, and in this way he created a kind of sea wall, protecting the coast from the strong waves. This story shows coastal erosion poses problems to humankind for centuries. After all, coastal erosion is a natural phenomenon. However, today it is exacerbated by multiple human-related drivers, such as the removal of sand, the deforestation, the urban expansion, the construction of coastal infrastructures, the unregulated greenhouse gas emissions, and so on. Climate changes greatly increases the risk we face in relation to flooding and coastal erosion, and it is time that all of us will acknowledge that we need to come together to try and change our course, protect our coasts and our seas from unsustainable fishing practices, unprecedented pollution, and tackle the devastating effects of climate change. Otherwise, we run the risks of fundamentally breaking entire ecosystems, of threatening our own lives and destroying the future of our children. There is a well-known saying in Silicon Valley that the best way to predict the future is to invent it. And that's what I want to do with you, with the people of our regions, by developing and implementing together a new strategy for tackling flood and coastal erosion. This new strategy can be summed up in one word, as proposed by Triton: resilience. Because while we always seek to protect people and property, we will not be able to prevent all flooding and coastal change, especially nowadays, since the climate crisis causes more violent weather, higher rainfall in shorter periods, and faster coastal erosion. So, we need to move from the narrow concept of protection or risk avoidance to the idea of risk management. Nature will always be stronger than us. We're obliged to work with nature rather than against it. That's why Triton proposes resilience instead of protection. To conclude, we all know that global climate change is one of the biggest threats of our generation, an economic, environmental, and national security threat. For my part, as the governor of the region of Western Greece, I commit myself to working together with all of you to catalyze new initiatives, raise awareness of the environmental changes we face, and step by step to advance a concrete plan on the steps we must all take to conserve the region's invaluable environment. I hope that today's event will inspire ideas, discussions, and solutions around the ways that we can make our region a resilient place. My remarkable colleagues here in the region of Western Greece have a great effort to prepare accordingly this final event of Triton. I hope you will enjoy the exciting speeches that are coming. Have a nice day, stay good and healthy. A resilient place.
Thank you, Mr. Farmakis, for your welcome speech. Now, the next speech will be from Ms. Tina Ranieri, Joint Secretariat Project Officer from the IDEREC project, which is funding the TRITON project. So, Ms. Ranieri, you have the word. Mr. Farmakis, for your welcome speech. Now, the next speech will be from Ms. Tina Ranieri, Joint Secretariat Project Officer from the IDEREC project, which is funding the TRITON project. So, Ms. Ranieri, you have the word. Mr. Farmakis, for your
Thank you. Thank you very much. Good morning to everyone. Kalimera. It's my pleasure to participate in this final event of TRITON project in my position of project officer. Thank you, first of all, to the regions and to the participants, the partners that give possibility for the implementation of the activities, and with a lot of success. Thank you. I will inform you about the program and connection between program and project TRITON. That give possibility for the implementation coordination of the activities and with a lot of success. Well, as you know, the cross-border cooperation program Greece Italy covers 4 regions. These regions are 3 in Greece, located in the west part of Greece, means the Western Greece region, the Epirus region, the Ionian Island region, and the Apulia region. These regions are 3 in Greece, located in the west part of Greece, means the Western Greece region, the Epirus region, the Ionian Island region, and the Apulia region. The 4 regional participants to the program cover the participation of 11 prefectures and 6 provinces in the Italy area. The 54% of the area is covered by the Greek region and the 46% by the Apulia region. 11 prefectures and 6 provinces in the Italy area. The 50% yes. Is covered by what I need to do? I don't understand. Yes. I cannot understand. Now it's better. Okay, thank you. Sorry. Well, I was speaking about the area of the program. Now for the budget, we have program as a budget more than 123 million euro. This has been, of course, 85% financed by the European Commission and 15% by the national government in Greece and in Italy. Well, as you know, the overall objective of the program is to support the cross-border cooperation for a more prosperous and sustainable region across the Ionian Sea. And for that reason, the program has been defined, taking into account the 11 thematic objectives described in the Common Provision Regulation. And as you can see, these 11 thematic objectives cross the overall objective of the program in terms of tackle common challenges and exploit the untapped growth potential in the border area. According to these 11 thematic objectives that are potentially all participated in the program in terms of activities and aims, the program chooses the 4 thematic objectives. Next slide, please. The 4 thematic objectives that are the base and the core strategy of the program. And you can see that this thematic objective as an important one for the project TRITON is the thematic objectives number 6, preserving and protecting the environment and promoting resource efficiencies. This is priority axis. Next slide, please. This is priority axis number 2 for the program Greece Italy. And this priority axis, after the first call of the program launched, and we will see results later on, has been the most important priority for both regions. I mean, from the region located in Greece and in Italy. And the priority axis number 2 is strictly connected with the thematic objective number 6. And for project TRITON, you can see also that the thematic objective transversal number 10 and number 11 are also very important for the project because both thematic objectives include education, skills, and lifelong learning by developing infrastructure. And also thematic objective number 11 is expressly oriented to enhance the institutional capacity and efficient public administration, and what this has been done with the project TRITON, and also for the efficiencies of the public administration and public services related to the implementation of the ERDF funds, and the support in action for the institutional capacity and the efficiency of the public administration. Well, as you can see, next slide, please. All the priority axes in the program Greece Italy have been declinated in specific objectives. And for what concerns the priority axis number 2, we have in our program 3 specific objectives. And you can see how the TRITON project, underlined in red color, is strictly connected with the objective specific number 2.2. This objective is oriented to the improvement of joint management and governance plans for biodiversity of coastal and rural ecosystem, paying attention on natural resources and protected area and development of environmental protection measures. Then the TRITON project is a specific project that would like an answer to the specific objective number 2.2, and as you can see, this specific objective is particularly important for the program, for the coherence of the program with the strategic framework of Europe 2020 and the user strategy. As you can see in the next slide, you have for the user strategy, please go on in the next slide, please. For the Europe 2020 strategy, we are working for a smart, sustainable, and inclusive development. And specifically, the project TRITON is strictly connected with the aim of preserving and protecting the environment and the promotion of resource efficiencies. After, you can see in the next slide, the user strategy, in which also there is a lot of attention and main importance of that particular axis, specific axis that is preserving and protecting the environment and promoting resource efficiencies. I would like to underline that the TRITON project is very important for the program Greece Italy because it's completely aligned about the core strategies of the program, about the 2020 strategy, the user strategy. And then we would like also to put in evidence that this project, last slide, next slide, please, is a project coming from the first call for ordinary project launched by the program. This call see the allocation of approximately 48% of the financial resources of the program, and 51 projects have been selected according to the results of the first call for ordinary project. And as I underlined before, an important number of projects, approximately 50%, 24 projects, were selected under priority axis number 2. This means that in the program Greece Italy, we have 24 projects dedicated to priority axis number 2, with, as I said before, more than 30 million euro. And as you can see in the left side, in the right side of the slide, for the specific objective 2.2, we selected at the program level 4 projects, and the TRITON project is one of these projects selected, and is specifically oriented for the coastal areas that are very important for the program, for our cooperation area. And then I will really appreciate the effort now after the implementation activities. We are in the last step of our project for the diffusion, for spread all the good practice and tools that have been developed by the project. Then I think that colleague and representative of both regions will be in charge now for explaining in details the results of the project. I thank you for your attention, and once again, congratulations for these results. Thank you.
Thank you, Ms. Ranieri, for all the information you gave for the INDEREC project. Now, I would like to welcome Professor Domenico Laforgia. Professor Domenico Laforgia is Director of the Economic Development, Employment and Innovation Policy Department of the Apulia region. He is the coordinator of the TRITON project. So, Domenico, please, you have the floor.
Okay, thank you. Good morning, everyone. First of all, I'd like to thank Mr. Nectarios Pharmakis, Governor of the Western Greece region, our partner in the project, on behalf also of the President of Apulia region, Mr. Emiliano. And of course, I'd like to thank all the other partners of the project, the University of Patras, the Network of European Cities for Sustainable Development, and the Euro-Mediterranean Center on Climate Change. Furthermore, I thank for help our regional agency, ARTI, and for the constant attention to our activities, the Joint Secretariat Interreg Greece Italy. The principal objective, this is a classical situation. The principal objective to reduce the consequences of TRITON, this is the principal objective, by improving the integration of the broader spatial planning and socio-economic policy in Greece. The specific objective of the project are to increase the cost effectiveness of decisions made in the field of coastline management, to reduce and optimize the expenditure for coastal data production and processing through common GIS and CIT web-based tools, to support a wider diffusion of better integration of coastal erosion concerns in planning and investment decisions through the adoption of environmental assessment instrument in every intervention proposal, either by the public or private sector, to transfer knowledge from the public sector to direct beneficiaries and investors, to balance the impact, cost and risk of human-induced coastal erosion, to assess common monitoring methodologies and mapping of risk tools to be incorporated into planning and investment policies for mid and long-term period. We expect strategic results as gradual improvement in the effectiveness of instruments for integrated spatial planning and coastline management in the areas of intervention, improved dialogue among the authorities of Greece and Italy, and cooperation during the project cycle and beyond, thus enabling better adjustment of the legal and spatial planning instruments, enhanced public awareness and involvement in coastline management issues for public and private entities as well as citizens, capacity building of the administration of both regional authorities as well as of stakeholders from civil society and private sector, networking of regional local authorities, administration officials, of universities and research center and civil society, a long-term contribution to a sustainable local business environment through better protection of the coastline from erosion. Content and goal of TRITON are well defined in the EU communication Blue Growth Opportunities for Marine and Maritime Sustainable Growth, aimed at developing the European strategy for the ocean, for the sea, and for the coast in terms of jobs, value, and sustainability. Apulia region, furthermore, participate at the European strategy for the Adriatic-Ionian region, you say it, which has the blue growth as first pillar to promote research, innovation, and change of business into blue economic sector. Giuseppe Pastore and Mrs. Michela Cariglia, project manager, and beautiful meeting. Thank you very much.
Okay, thank you, Professor Lafoggia. Now, the next speech will be from Giuseppe Pastore. Giuseppe Pastore is Director of the International Promotion Office Economic Development, Employment and Innovation of Policy Department from Apulia region. His speech will be about the TRITON project overview and results. So, Giuseppe, you have the floor.
Thank you very much. Can you hear me, first of all?
Yeah, we can hear you. You can.
Okay, perfect. Now, good morning, everyone. As you also said, I am Giuseppe Pastore, head of the International Business Promotion Office of the Economic Development and Innovation Policy Department of Apulia region. And once again, thank you to the organizers and the other speaker, the organizer of this beautiful final event. And so we are here today to present the TRITON project. And this final event is definitely, it's quite atypical because of the difficult historical moment we are going through due to the emergency. And we had to reformulate various activities and to change very quickly the way we are used to operate. The office I manage traditionally is engaged in activities such as fairs or incoming or outgoing missions and attraction of investments. Now the office is trying to develop new tools and alternative instruments to support companies and small and medium enterprises. So we are trying to develop alternative solutions, for example, the e-commerce solutions or the digital export. So these circumstances have not prevented us from carrying out our project until we have completed our activities. So let me tell you briefly something about TRITON. Well, then my colleagues will go into the more technical aspects of the project. TRITON derives from the need to reduce the consequences of coastal erosion and improve the planning of the costs in the areas involved in the project, Puglia and Western Greece. These regions, in fact, must face the effects of erosion due to natural causes and the human interventions. Despite the protocol of integrated coastal zone management of 2008, problems remain and affect people and ecosystems. So the protocol approach and the principles are adopted in both countries, but there is a need to further support the implementation of integrated coastal zone management. So the project was financed by the Interreg BA Greece-Italy 2014-2020 under Priority Access 2, which deals about the integrated environmental management. The project started in April 2018 with a little delay, but we have recovered it very quickly because of the quality of the people involved in the project. Apulia region, as you know, is the lead partner with the technical support of ARTI, which is our agency for innovation and technological development. Today with us, there are all our partners, which are the CMCC, the Euro-Mediterranean Center for Climate Changes, the region of Western Greece, ex-Finipoli, which is the network of European cities for sustainable development, and the University of Patras. I will give you only a quick overview on the results of the project, on the activities carried out, and also on what has been done in terms of training and education. Then my colleagues will tell you more about the technical aspects. Certainly, the TRITON project has contributed to the development of the administrations and the stakeholders involved in coastal management. The networking between Greece and Italy and between technicians and research centers increased our cooperation on territorial. So we have produced the studies that analyze the state of the art of coastal management and coastal erosions in the interested areas, with a focus on the practices implemented in specific pilot areas identified in Western Greece and in Puglia. Specifically, we have identified 3 successful pilot cases in Patras, Ugento, and Bari. And these cases have been identified and represent 3 virtuous ways of dealing with the phenomenon of coastal erosion through economic, legal, geological interventions. We have created a platform with maps, documents, materials, and educational videos about coastal planning and mitigation of coastal erosion. We had 2 international summer schools on the management of coastal areas for local administrators and professionals on the 24th, 25th, and 26th of September 2019 in Patras, and on the 1st, the 2nd, and the 3rd of October 2019 in Bari. We also had some training days on coastal planning in Bari on the 18th of October and in November 2019. Now I don't want to leave, I don't want to take any other time, and I leave the floor to my colleagues. Each partner will present you specifically their own activities. I hope you enjoy these hours together, and if you have any questions, feel free to contact us. You will find my address and phone on the institutional site, www.internazionalizzazione.regione.puglia.it. Thank you very much. Hope you find and enjoy the final event.
Thank you, Giuseppe. Now, we are passing to the technical presentations of the project. All the partners will present in the next couple of hours the technical results from the TRITON project. The first two presentations have been prepared from the lab of the University of Engineering, of the Laboratory of Engineering Geology, Department of Geology. The first presentation, I will make a search now. All right. The first presentation has to deal with the establishment of a pilot erosion observatory in the Gulf of Patras. It's a presentation prepared by me and Professor Sabatakakis. It doesn't. Sorry for that. Okay. So the aim and objectives of a pilot erosion observatory is exactly to establish an observatory in areas which deal with significant erosion problems and aims to collect real-time data for monitoring of several parameters that negatively affect shoreline, and collect data later can be used with the appropriate interpretation for the design of long-term protection measures of the suffered shorelines. In order to achieve this goal, it is necessary to create from the early beginning a detailed geomorphological and coastal plan of the study area and install the necessary equipment for real-time monitoring. So, the pilot area for establishing this erosion observatory is the Gulf of Patras from the Greek side. The Gulf of Patras was selected as the study area for the establishment of this erosion observatory because of the existence of a main port connecting Greece-Italy, which is the new port of Patras that connects Patras with Italy. The increased urban and touristic development that is gradually expanding along its shoreline, and the existence of rich biodiversity in the Gulf of Patras. The activities engaged for the establishment of this pilot erosion observatory had two main parts. The first part was the equipment installation performed by the region of Western Greece. So during this installation, one wave data buoy system for wave intensity measurements installed in the Gulf of Patras, two tide gauges maregraphs for sea rise level and tidal measurements installed in the new port of the city of Patras, and two weather stations for real-time atmospheric measurements were installed in the port of Patras and the port of Kyllini. The one tide gauge for sea rise level and tidal measurement installed in the new port of city of Patras, and the other one installed in the port of Kyllini. Additionally, surveys and studies performed in the Gulf of Patras by the University of Patras, by the team of the University of Patras. All these surveys and studies that were performed comprising geotechnical surveys and engineering geological plans, satellite aerial photo imaging, UAV and USV surveys, marine surveys and digital bathymetric plans, environmental monitoring in the protected areas, and finally, numerical study of waves, currents, and sediment transport. Concerning the equipment installation, as you can see here from the Google Earth image of the Gulf of Patras and generally of Western Greece, one weather station and one maregraph was installed in the new port of the city of Patras, and the wave buoy system installed in the deep waters of the Gulf of Patras. Additionally, in the western part of the region of Western Greece, one weather station was installed under Marigraph in the Kyllini port because we had to deal with erosion processes along this part of the coastline from Kotichi Lagoon up to Kyllini port in the western part of the region of Western Greece. As I said before, the installation was completed by the region of Western Greece, and all the studies and surveys have been completed by the University of Patras. So now I would like to present you a few diagrams and results of this equipment. This equipment started to operate from October 2019, and concerning the weather station in the new port of Patras, it provides real-time atmospheric measurements such as temperature, humidity, wind speed and wind direction, and rain height. Here is a photo, an image of the weather station. And in the right side of the picture, you can see the Windrose diagram for covering the period from 1st of January up to the 15th of April 2020. From this diagram, you can see the main wind speed and the main wind direction in this part of the Gulf. Additionally, a Marigraph, a tide gauge, has been installed in the new port of Patras. Again, this equipment installed on October 2019 and provides real-time sea level and tidal measurements every 10 minutes. Here you can see this type of equipment and the diagram showing the sea level measurements for the same period, for 1st of January 2020 up to 15th of April 2020. You can see the sea level rise. The maximum sea level rise is 30 centimeters. So with a real-time monitoring, we can check which is the sea level rise due to tidal measurements or due to the fact that sea level rises the last years. So this equipment is operating and sends data every 10 minutes to the database of that we have installed. Now, concerning the wave data buoy system that has been installed in the Gulf of Patras, you can see here this system. You can see this system here. It has been installed in the deep waters of the Gulf of Patras. It provides real-time wave measurements every 30 minutes. And which are the diagrams we can have from these measurements? You can see in the left side of the picture, the wave height, the significant wave height for the period 2020. As you can see, the maximum wave height is up to 1.1 meters and has been occurred between the end of January and another has been occurred at the beginning of March. So the maximum wave height that we observed in the Gulf of Patras, where the buoy system has been installed, is 1.1 meters. Again, this system can operate and give us which is the main wind direction, as you can see in the Windrose diagram, for the same period. As we move towards the west side of the region, move towards Kotichi Lagoon up to the Kyllini port, another two installations of equipment have been made. The one is the weather station. Again, you can see Windrose diagrams for the same period, which is the wind speed in meters per second, which is the direction of the wind. And the water level measurements which in the case of Kyllini Port, the maximum water level rise is up to 0.22 meters or 22 centimeters for the same period. Again, you can see this picture, another maregraph that has been installed in the Kyllini Port. This type of equipment is very important for us because it's the first time that we can have real-time measurements for all the studies that can be performed for coastal engineering processes. So, concerning the other partner of the group, which is the University of Patras, it's very important, apart from dealing with all these real-time measurements, to make all the necessary preparations and plans for the Gulf of Patras. So these surveys and studies comprise geotechnical service and engineering geological plans, satellite aerial photo imaging, UAV and USV surveys, marine surveys and digital bathymetric plans, environmental monitoring and management, and numerical study of waves, currents, and sediment transport. I will very briefly give you which is the University of Patras research team that dealt with all these surveys and plans. Professor Nikolaos Sabatakakis, who is the project manager, and I, as a deputy project manager, we searched and we had the surveys concerning the engineering geology information. Professor Konstantinos Nikolakopoulos, who is the member of the technical committee, searched for the remote sensing and GIS. Professor George Papatheodorou, who is the member of the advisory board of the TRITON project, Marine Geology and Oceanography. Professor Athanasios Dimas, member of the advisory board with Coastal Engineering. Of course, apart from all these professors, we had the external expertise and researchers in our teams, Dr. Dimitris Christodoulou, Dr. Elias Fakiris, Dr. George Lefteriotis, and Dr. Katerini Kavra, and two PhD candidates, Vasilios Bouboulis and Dionysios Apostolopoulos. So as you can see, we have a very big research team with all the necessary scientific experts and fields, because as you can imagine, to deal with erosion processes and with coastal engineering, it's not just a simple aspect. It has to deal with a lot of things. So before going to the next presentations, where my colleagues and all the partners who investigated all these surveys, I will give you very briefly just a picture of what is a geotechnical survey, a remote survey, etc. Concerning the geotechnical surveys that were performed along the shoreline of the Gulf of Patras, we made borehole drilling and core sampling along the shoreline, in situ and lab tests, sediment analysis, and the purpose of the geotechnical survey program was to identify the soil stratigraphy and the geotechnical properties of the coastline for specific coastal applications. As you can see in this Google Earth map, represents the geotechnical operations performed along the shorelines. You can see the dots, the red dots were the boreholes, the yellow dots were the sediment sampling, and square dots were the CPT tests that were performed along the shoreline. The second main part is the satellite aerial photo imaging and UAV and USV surveys. So for making a very detailed satellite plan, aerial photo imaging, and to understand which is the shoreline displacement, all of these several satellite and aerial photo imaging were processed from 1945 up to 2008, and equipment that was purchased in the frame of the TRITON project were used for data collection in specific areas. The third part of the surveys comprised marine surveys and digital bathymetric plans in order to calculate and to deal with efficient numerical modeling for coastal engineering processes. An extensive marine survey was conducted, comprising of marine research and data acquisition methods for mapping the bathymetry of the southern part of the Gulf of Patras, processing and analysis of the collected data, and finally, bathymetric plans of the research area. And finally, environmental monitoring and management, which is very important. As you can see here in this satellite image from Google Earth, apart from the installed equipment of the TRITON project, the managed body of Kotichi, Strophilia wetlands and Kyparissia Gulf provided us their stations in the Papas, Prokopos and Kotichi lagoons. These stations are monitored by the management body, and we have access to the data that have been collected in these three lagoons. So, as you can see, we have a completed network of environmental stations, which starts from the Kyllini port and ends up to the port of the city of Patras. Finally, all these supported investigations at SFERDIS end to a numerical simulation of waves, currents, and sediment transport. In order to deal with this numerical simulation, all the investigation area, the Gulf of Patras, has been divided to 8 sub-regions. So the numerical simulations includes 4 stages: determination of wave climate, simulation of wave propagation, simulation of the magnitude and direction of the wave-generated currents, and numerical simulation of the magnitude and direction of sediment transport. All these surveys and plans are going to be presented in the next presentations from all the partners, all from the research team of the University of Patras. So I will pass right away to the next presentation. Okay. Okay, as I said before, the first presentation concerning the geotechnical surveys in the coastal zone of the Gulf of Patras has been prepared by the research team of the Laboratory of Engineering Geology, Department of Geology, University of Patras. The members of the laboratory that had the investigation in the Gulf of Patras concerning the geotechnical investigation is Nikolaos Sabatakakis, Professor of Engineering Geology, I, Assistant Professor of Engineering Geology, Katerini Kavora, Postdoc Researcher, and Vasilios Bouboulis, PhD candidate. So, as I said before, the University of Patras had the second part of the project concerning the Gulf of Patras, surveys and studies performed by the University of Patras, and the Laboratory of Engineering Geology collected all geotechnical data and made all the necessary geotechnical surveys and engineering geological plans. Later, the other colleagues will present you about the satellite marine surveys and numerical study of the investigation area. So, it was very important from the early beginning to collect all data, all the necessary data from along the shoreline of the Gulf of Patras, starting from the Araxos Cape up to the Glafkos River. One very important aspect is to collect very detailed, to have a very detailed framework to collect sediments along the shoreline, which is very important for numerical studies and sediment transport. Secondly, to drill boreholes along the shoreline to understand which is the geological basement of the coastline of the Gulf of Patras. And finally, to make all the appropriate in situ and lab tests. The purpose of the geotechnical survey program was to identify exactly which is the soil stratigraphy and the geotechnical properties of the coastline of the Gulf of Patras in order to proceed later for specific coastal applications and constructions. During the project, 6 specific boreholes were drilled along the shoreline. Soil core sampling has been made. In situ tests, SPT, standard penetration tests, were performed, as well as the necessary laboratory tests. Here you can see the type of equipment that was used for this drilling process and an example of the samples which we have collected along the shoreline. As you can see in this box, the first 2 meters, it's mainly sand and gravels. And as we go into the deeper horizons of the coastal zone, we can see that we have silt and clays. So after we made also on-site macroscopic examination of all soil coil samples, recording, we moved these boxes, photographed them, and transported to the lab for testing. It was very important for us to make, during this drilling process, all the necessary in situ tests. This is very important when you are dealing with coastal zone, because the samples that are collected from the soil boxes many times are not appropriate for tests, for lab tests. So from the early beginning, we had designed a very detailed in situ program testing comprising of standard penetrometer tests. As you can see here in this photo, this type of test has these aluminum tubes, and at the end is a collector, and we're hitting this collector deep in the ground, and from the resistance we can understand which type of soil, if it is sand, if it's clay, or if it's silt. So depending on the resistance of this soil tube, we can understand which type of soil we can find deeper from the surface. The final borehole log from the drilling process is like this one in this picture. Here you can see in the left-hand side the soils that have been drilled. And in this diagram, the type of SPT results, which is the resistance exactly during this SPT in situ test. So apart from this borehole logs and the test we performed along the shoreline, we collected several borehole logs, lab tests from other past researches, because we had to collect them in a database, in the geotechnical database, to understand which is the exact geotechnical behavior of the coastal zone. Very important during this survey was the cone penetrometer test. The cone penetrometer test has to deal with the penetration of a cone, a simple cone, deep into the ground. And during this process, we can measure the resistance of the soil tip, of the tip of the cone, and make the necessary pore pressure measurements of the soil. So As we're dealing with this cone penetrometer test, here you can see the compression cones. Is a cone that has a very sharp tip at the end, and this is squeezed into the ground, and it gives us results like that. Here you can see which is the final result from this process. We are taking a diagram which provides us details about the cone resistance, and with the appropriate interpretation, we can estimate which is the soil horizon during this process. For example, the blue one, here you can see the picture, is mainly clay. That's why soft clay, we have a very smooth and a very low resistance. And on the other hand, the orange color is sands. That's why this is the reason why in the diagram we have a sharp and very high measurements about the cone resistance. Here you can see the photo. This vehicle is an automated vehicle, and from which we can make this drilling process, this deep into the ground. Very important for us was to find an appropriate area to make these tests. We selected mainly to make these tests the Kato Achaya beach area, which is from Niforeika up to the mouth of the Pyros River. This was nearly 3 kilometers in length. And so we decided that was a very important area for us to understand which was the bedrock and the soil deep, the soil in this area. The third aspect during this geotechnical survey program was sediment sampling and grain size analysis. Shoreline for sediment sampling for coastal engineering purpose and sediment mapping has been made. So what we did along the shoreline, we collected nearly 102 samples along the shoreline of the Gulf of Patras. The samples were from the coast and deep in the water, up to 2 meters deep, in order to have a very good profile of which is the grain size distribution along the shoreline. So we made all the necessary laboratory identification classification tests with an emphasis given in grain size analysis. And we find which was the representative D50, the 50% diameter of this grain, in order to pass all these results to, as you can see later, to our colleagues to have the necessary numerical simulations about the sediment transport. Here is an example of a sediment map in the Kato Achaya beach. So, for example, here in this area, we had a very fine grain size, silt to clays. And in contrast, in this area, we had grain sizes from sands to gravel. And as you can understand, the erosion process is completely different here in this side compared with the erosion process here in this side, because the erosion is higher when we have fine grain material and lower when we have grain size material with a bigger diameter. But of course, there is another combination with wind speed and currents, which is going to be explained by Professor Dimas in a later presentation. Concerning the some geotechnical things that is very interesting for constructions, especially for constructions activities, if you want to make protection measures along the shorelines, is the liquefaction potential index. it is necessary to map and identify hotspots of liquefaction in order to avoid them. So from this shoreline, which is part again of the shoreline of Kato Ahaya Beach, we can see that this area is not appropriate for constructions because soil can be liquefied after an earthquake, and either we have to avoid this area for construction, or we have to deal with a more expensive construction measures, such as improve the soil density in order to make a construction here in this area. So that's why this is very important for shoreline constructions, the liquefied potential index. Finally, after gathering all these results, geotechnical data, grain size analysis, we managed to make a plan along the shoreline of the Gulf of Patras, where we are presenting all the engineering, geological or geotechnical units according to the grain size distribution and the geotechnical properties. Very briefly, here you can see along the shoreline, it's a very thin layer of sands, gravels, silts and clays in some parts. As we're going inside the mainland, we can find bedrock in these positions, or we can find recent deposits in these positions, or older deposits, fine marls in these positions. This is very important, especially if local authorities want to make plans for residential development or other constructions. So they have to know from the early beginning which type of soil they're expecting in each area and what might be the necessary constructions on this type of soil. Here you can see from these maps, we can make several geotechnical cross-sections. If we know exactly all the soil units, thickness, geotechnical properties, we can make cross-sections of this type. For example, in this geotechnical cross-section, you can see with the yellow color coarse-grained soils, and with this gray color, fine-grained soils, salt silts, and clays. Again, this is very important when dealing with constructions. So, by concluding this presentation, I will make a summary of the geotechnical implementations in the area of intervention. So, first of all, we determined the physical and mechanical properties of the coastal geological formations. We managed to start to make an efficient determination of the erosion sensitivity of these formations, and in order to make coastal engineering necessary precaution measures in the area of intervention. We are trying, after gathering these results, to improve the coastal vulnerability modeling with the initiation of geotechnical data and graded indexes, assess the liquefaction potential index along the coastal zones, make all the necessary design of geotechnical cross-sections for shoreline infrastructures and foundations. And finally, the final aim after ending this project, because apart from dealing with the project, you have to see the next step. So the final aim after the end of this project, it is the use of results, information, and data for the production of maps and diagrams in order to detect any potential geological hazards and erosion threat across the shoreline that may affect future construction activities and residential development. So these were two presentations from the Laboratory of Engineering Geology. Now, according to the program, we will see a video presentation about coastal planning in Patras, and later we will go to the next speech from Associate Professor Konstantinos Nikolakopoulos. So please, if you can give in the screen the video presentation number 1 about the coastal planning in Patras.
The coastal areas of Western Greece are affected by widespread coastal erosion, causing social and economic problems as loss of coastal land, destruction of coastal infrastructures, and impacting our tourism industry through partial or total loss of beaches. According to studies, the phenomenon of erosion is becoming more pronounced in specific areas of the municipalities of Patra, like Monodendri, Vrachneica and Tsoukaleica, and West Achaia, like Niforeika, Kalamaki and Alissos. Indeed, in some areas from 1965 until today, beach widths of up to 26 meters have been lost, while the river Pyros has lost estuaries of 100 meters wide. The region of Western Greece is involved as a partner in the implementation of the TRITON project, funded by the Interreg VA Greece-Italy program 2014-2020, and is installing one weather station and one tide graph in each of the 2 selected areas, Patras New Port and Kyllini Port. At the same time, it is planned for mid-October to be installed in the marine areas of Patras New Port, the first wave data buoy system in the region of Western Greece. Moreover, employees of the region and the municipality of Patra, as well as PhD students, participate in the summer school organized by the program leader, the Apulia region, to train them on coastal erosion issues, technically, financially and legally.
We are here in Kato Achaia Beach. Is one area part of the TRITON project. We're very interesting about this area because it's exactly in the middle of the Gulf of Patras. The decision to have this research area and to have as a pilot area the Gulf of Patras because across the coastline, which is 50 to 55 kilometers long, we have detected serious problems of erosion, not erosion all along the coastline, but in different parts. So, one part of our project is to investigate with geotechnical means what's happening here. Other part of the project is to investigate it with marine studies, and another one with remote sensing and shallow water surveys. So, what exactly we are doing here? We have all our equipment, penetrating the ground and see what is happening with the properties of the soil. And the other thing is to detect areas where the sediment is being transported through high waves or currents and detect which areas need more protection. So, by concluding, the Gulf of Patras is very important for the city of Patras and the local authorities, the region of Western Greece, because it's the most dense populated area in the region. A lot of activities are performed, like touristic activities, building activities, and other commercial activities. And in the western part of the Gulf, there is a protected area, a very big fishery protected area. So it has all the necessary elements like environmental, anthropogenic and other elements which are very interesting to us. So by concluding and having in mind that climate conditions are getting worse over the forthcoming decades, we have to take an exact picture of the Gulf of Patras, monitor what's happening inside the Gulf and along the shoreline, and decide which is the best protection measures to protect environment and anthropogenic constructions.
Generally speaking, the coastal environment is a very fragile and sensitive environment and is controlled by a number of factors. For instance, it's very important to know the sediment budget. I mean the supply of the sediment from the river. Another very important factor is the coastal processes. I mean the waves, the longshore currents, the tides, and the meteorological parameters, for instance, the winds. The climate change is another factor that may affect the coastal environment. And finally, we have the anthropogenic impacts. We have a lot of offshore construction and coastal construction that finally heavily affect the morphology of the coastline. In the Patras Gulf and particularly at the southern border, at the southern coastline of Patraikos Gulf, we carried out a preliminary survey in the framework of TRITON project. And we defined some areas that have been heavily affected by the erosion. And the causes, the main cause of the erosion in the area is mainly the anthropogenic factor, the anthropogenic impact. We have a very high degrees of the sediment supply from the rivers due to the illegal dredging of the material at the delta of the river, and we have a lot of dams that we have constructed upslope of the river. A very important and crucial point is that we have no scientific data regarding the coastal environment in order to design the protection of the coastal environment. That's why, in the framework of the European project IDEREC, TRITON, we are going to carry out a very systematic survey using state-of-the-art geophysical equipment. We are going to collect very detailed bathymetric data. We are going to collect very detailed morphological data from the sea floor, and we even define the seismic stratigraphy, I mean the subsurface structure of the seabed. At the same time, we are planning to deploy a wave recorder at the area in order to have a very complete data set regarding the waves. And of course, we are going to deploy a meteorological station and the tide gauge in order to record the tides of the area. So all these integrated data set will be valuable for the protection of the southern coastline of the Gulf of Patras.
Professor Konstantinos Nikolakopoulos will demonstrate equipment we are using for the TRITON project. Drones and this small boat over there. Drones is to take in aerial photographs, to map all the shoreline today, and to make comparisons with previous aerial photographs from past years. And the small boat over there is to have a scan of shallow water bed.
So we will perform a photogrammetric flight in the Gulf of Alikes. That means that we have designed a grid. The drone will go up at 100 meters and will take images at very specific points designed in previously with a photogrammetric grid. And after that, at the office, we will process the data and we will create orthophoto map of the broader area and also a very detailed digital surface model of the land and of the shallow water. We can have an accuracy of 2 or 3 centimeters with this procedure, both in land and in the shallow water. Okay, we also perform measurements with the differential GPS in order to georeference the data from the drone and from the unmanned surface vehicle.
For the purposes of the TRITON project, we use highly sophisticated equipment. One equipment we are using is a cone penetrometer equipment test. Another in the future is a geotechnical boreholes, another equipment which is part of the TRITON project.
And I will say a few words about the good remote sensing practice for contrasting coastal erosion. What we do in the frame of TRITON project. First of all, we use air photos and digital satellite data in order to monitor the coastline erosion from 1945 till today. A lot of remote sensing processing techniques are used in order to detect how the coastline retreat for the last 73 years. Secondly, we use unmanned aerial vehicles, more known as drones, in order to perform photogrammetric flights along the beach in specific places in order to map with a very, very big accuracy the coastline. Also, we use an unmanned surface vehicle, a small vessel, with a side scan sonar and also with a very accurate sonar in order to map the seabed. We try to map the shallow water environment, that means from the coastline up to a depth of 5 meters. And finally, we will create a geodatabase in order to integrate all the data, remote sensing data, marine geology data, and engineering geology data in a common geodatabase in the frame of TRITON project.
The Interreg Greece-Italy program is a very important program, and we're very happy to work with the Puglia region on this scientific technical issue. We expect the results to be very useful for our societies and for our region and both of our countries.
Okay. Now we are passing, before passing to the next speech, I would like to remind you that you can use the chat tool where you can send all your questions for later discussion at the end of this event. So now we are moving to the next speech. The next speech is remote sensing applications in the frame of the TRITON project. Associate Professor Konstantinos Nikolakopoulos, coming from the Department of Geology, University of Patras, will give this presentation. So please, Professor, you have the floor.
Good morning. Thank you, Professor Depoudis. I will talk to you about the remote sensing applications in the frame of TRITON project. The team from the GIS and Remote Sensing Laboratory who worked in the frame of the project, it's the speaker, and also Mr. Dionysis Apostolopoulos and Mr. Dimitrios Konstantinopoulos. Both they are geologists and they are working in the frame of TRITON project. We used a lot of satellite or a lot of remote sensing data, medium to very high resolution satellite data, historical photos, also data from a small autonomous vessel, and also aerial photos collected from drones from unmanned aerial vehicles. I will tell you a few words about the connection between the remote sensing spatial resolution and the map scale. So there is a mathematical formula connecting the spatial resolution of remote sensing data to the map scale. For example, if we have an air photo with 1 meter pixel size, then we can produce a map at the scale of 1 to 2,500 scale. You will see here some examples of the data that we used in the frame of TRITON. This is a Sentinel image with 10 meter spatial resolution. The area is in Alikes beach, the area who took place the training during last September. So we can see here Alikes port with a resolution of 10 meters, and we can produce a map at a scale of 1 to 25,000. This is from the same area, a respective image from an air photo, an historical air photo. The spatial resolution is 1 meter, and we can produce ortho photos at a map scale of 1 to 2,500. This is an example of worldview data. We purchased those data in the frame of TRITON, and those data were acquired on September 2018. We can produce maps up to 1 to 2,000. Data from the Greek cadastral that we used, also photos from the Greek cadastral with a resolution of 25 centimeters, and so we can work at a scale of 1 to 600. And finally, UAV data. Here the spatial resolution is 4 centimeters, so we can work and produce maps at a scale of 1 to 100. For the medium resolution satellite data, we assessed the suitability of Landsat 8 and Sentinel MSI data for the coastline extraction, and we estimate the accuracy. The basic advantage of this data is that they are freely available through internet. So we wanted to examine their accuracy and if they are appropriate for studies in the coastline. The steps for the processing of medium resolution satellite data. First of all, we create a panchromatic band. We simulated the panchromatic band for Sentinel data. Then we perform data fusion in order to improve the spatial resolution of the data. And then we used indexes, band ratios, like the normalized difference vegetation index and the normalized difference water index in order to automatically extract the shoreline. Here is the simulated band of Sentinel-2 data. We have created this band. This band has a spatial resolution of 10 meters, and we can see the city of Patras and the new and old port of Patras. Here is the multispectral image of Sentinel data with spatial resolution of 20, 30, and 60 meters. Different bands have different spatial resolutions. And here is the fusion result. As you can see, we have improved the spatial resolution of the image. And in the next slide, you can see the two images in comparison. At the left, we have the original image, and at the right, we have the processed image. As you can see, the spatial resolution, the analysis of the image is better, so we can more easily extract and detect the shoreline and the human construction on the shoreline. Then, using different band ratios and different indexes, like the normalized difference water index, we managed to extract to divide the image, to classify the image in two classes, C and LAD, and to extract the shoreline. Here is an example of Landsat 8 image. Here is another example of Landsat image using the normalized different vegetation index, another band ratio for the classification of the image between land and sea, and the Sentinel NDWI, the normalized difference of water index. So we've managed to create the shorelines, to extract the shorelines from Sentinel and Landsat data, and to compare their accuracy with the more accurate data from Worldview 2 data, the very high resolution data that we purchased in the frame of TRITON project. Last week, we also published a paper about the accuracy of the data. And as you can see in the image at the left of the slide, there is a displacement between the shorelines that we extracted from Landsat 8 and Sentinel-2 data in comparison with the Worldview 2 data. Furthermore, we used very high resolution remote sensing data in order to map the diachronic evolution of the coastline for the period from 1945 to 2018. That means a period of 73 years. For this purpose, we used air photos, historical air photos from the Hellenic Geographical Military Series, air photos from 1945, from 1960, from 1996. We used also satellite imagery with high spatial resolution from 1973 and very high spatial resolution data from GeoEye and Worldview 2 from the years 2012 and 2018. We also rectified all the remote sensing data using Leica photogrammetry suite software. You can see here an example of the processing of the Worldview data, different scenes along the coastline of the Gulf of Patras. And here we have the final orthophoto. As you can see, the area starts from the cave of Rio to the cave of Araxos at the west. You will see now some examples of the remote sensing and GIS processing of the data. For example, for the area of Rio, we can see an air photo of 1945 and with red color the coastline of 1945. Here is the same coastline from 1945, but the background is an air photo of 1996. You can see that there is an erosion in the area of Rio, and in digital satellite image from 2012, a GeoEye image, and with the coastline of 1945 with red color. You can see the changes in this part of the image. You can see the changes at the shoreline evolution. We have erosion in a part of Rio and also a human construction, the port in this area. In a bigger scale, in a higher scale, here we have for another area in Rio at 1 to 1,000 scale, the image from 1945, the image from 1996, and the image from 2012. With red line, we have always the coastline, the shoreline of 1945. So you can see that we have intense erosion during the period of 73 years. For specific areas, we also used UAV data for monitoring specific shorelines in areas where we have noticed that there is an intense erosion. Here is an example of the UAV data processing using Agisoft Photoscan professional software. At the left, it's the processing of the data, and at the right, it's the orthomosaic of the Alixos area, Alike Sport, where the training took place last September. Also, an example from UAV flights in the area of Rio. We took thousands of photos and we create a very big orthomosaic covering the area from Rio to Avenue Kanelopoulou, about 2 kilometers distance along the coastline. Also, we used an unmanned surface vehicle, a small vessel, equipped with 2 sonars, a very accurate sonar, and also a side scan sonar. This was used in the shallow water in areas where the big vessel cannot make surveys. Now some results from our processing. You can see here a photo of the whole coastline in the Gulf of Patras, the whole study area. With red color, you can see the areas where the erosion was higher than 30 meters during the period from 1945 to 2018. And with green colors, the areas where the accumulation was higher than 30 meters. In more details, we have noticed that in 8 areas, and more specifically Araxos area, Karnario area, Kalamaki, Niforeica and Talikes, Yalos, the new port, the old port, and Rio area have intense erosion or accumulation phenomena during the 73 years period. Here is a characteristic example of how the coastline monitoring is a quite complex phenomenon. Here in Araxos Cave, we observe that we have in the same area erosion and accumulation. So with red colors, we may notice that the beach has been eroded about 94 meters. That means a rate of 1.28 meters per year. And a few meters away in the eastern part of the cave, there is a strong accumulation of about 333 meters. That means a rate of 4.5 meters per year. I will show you some examples of the accumulation erosion in the same area. Here we have an orthophoto of 1945, and with red color we have the shoreline of the same year. Here is an orthophoto, an air photo of 1970. You can see that at the west part of the cave Araxos we have erosion, and at the same time at the eastern part we have accumulation. This is the cadastral image of 2016, and the red line is still the coastline of 1945. And here we have the gold view image of 2018 and the coastline of 1945. So you can see that along a few meters, we have in the same area big erosion, a big accumulation. The second site is Karnari Beach. It's the same phenomenon we have both erosion and sedimentation. So we have we have noticed that we have an erosion of 1.07 meters per year, and at the same time, we have sedimentation in the western part of the area equal to 130 meters or 1.5 meters per year. Here is the Kalamaki beach, the third site. You can see inside the yellow box a seagull in front of the local resort. And you can see that this construction has stopped the erosion in front of the seagull, but we have erosion problems at the west of the construction. Niforeika Beach, we have the same phenomenon, erosion and accumulation, changes between erosion and accumulation. Also, this is the fifth site, Yalos Beach. Here, the mean erosion has overpassed 1.15 meters during the 73 years period from 1945 to 2018. And we believe that in the next year, here the phenomenon of erosion will become more intense as a dam was built in Piro stream. And so we believe that the erosion will be more intense. Here is a characteristic example of the human intervention in the coastline, the old and the new port of Patras. You can see at the left an air photo of 1945 and with red color the coastline of today, and in the right part of the slide you can see a satellite image of 2018. You can see that we have a construction, the new port of Patras has increased the shoreline for more than 226 meters. That means an accretion rate of 3.12 meters per year. And finally, the Rio area, there is an alternation of accretion and erosion of a rate of 0.15 meters per year, and the construction of the pier at the left of the image has led to the erosion further east due to the obstruction of the coastal currents. These are the results of the remote sensing application in the frame of TRITON project. Thank you very much for your attention.
Thank you, Professor Nikolakopoulos, for the very interesting presentation. Now, we are going to the next presentation. The title is The Contribution of Multi-Beam Shallow Water Bathymetry Mapping on the Coastal Erosion Surveys in the Gulf of Patras. The theme of this presentation is the team is Professor George Papatheodorou, Dr. Dimitris Christodoulou, Dr. Elias Fakiris, coming from the Department of Geology, University of Patras. And the presentation will be made by Dr. Elias Fakiris. So, Elias, you have the floor.
Hello, everyone. Let's share my screen. Sorry. Okay, I'll share the other screen. Is it okay? Great. So, as Professor Deputy said, I'll present the contribution of the multi-beam shallow water bathymetry mapping on the coastal erosion surveys in the Gulf of Patras. The team has as well been presented. So let's start with some principles about what multi-beam echosounder is, and generally how sonar bathymetry is being performed in the deep or shallow waters. Actually, traditionally, bathymetry in underwater is performed through sound, through echosounders, which are transmitters that send sound beams from the vessel to the ground and then back to the vessel. They're being recorded, and by the time the sound needs to travel from the vessel to the ground and back, we can estimate the depth below the vessel. In the more old systems, only one beam was transmitted by the transmitter, so only a small footprint below the vessel could be recorded. Nowadays, we use multi-beam echosounders, which are actually nothing more than echosounders that transmit multiple beams along a swath, and so we can record bigger parts of the seabed and make a more detailed and full coverage bathymetric map of the seabed. The applications of multi-beam echosounders span from engineering, underwater coastal engineering, like pipelines or breakwaters. It can also be used for cultural heritage, underwater maritime cultural heritage reasons, such as wrecks, as seen here, or for habitat mapping. Actually, habitats constitute a very important seabed feature, which can be detected through morphological parameters. So you can see some point clouds of the underwater of the seabed, where you can see some patches of seaweed, like Posidonia oceanica, or a more detailed map where this texture, characteristic texture, can help us classify seagrasses on the seabed. Now some words about the types of multi-beams and their mounting. There are actually two types of multi-beams, the deep water ones and the shallow water ones. The deep waters are using very low frequencies of sound, and they're big instruments, so they have to be mounted on big vessels through expensive works. But in coastal waters, there are more portable equipment, like this one, that can be mounted on small research vessels. So this was the case in Patras. However, there are other options for even shallower waters, like vessels of opportunity, small vessels, or even jet skis and kayaks. As Professor Nikolakopoulos said, we also used an unmanned surface vehicle, such as this. Okay, this is just an example. The principles of multi-beam echosounder surveying is that we conduct consecutive parallel lines along the area that we want to survey, so that each swath, its coverage that the multi-beam produces will have an overlap with the next coverage. So each line has a coverage with the next line, and at the end we have a very full resolution and full coverage bathymetric map. Now, the main question is, why do we need bathymetry in studying coastal erosion? Until now, we mostly said about the coastal parts of the survey that is needed to monitor erosion, coastal erosion, but now we'll see why we need also the underwater part of the coastal zone. So, if we want to monitor the vulnerability of a beach to erosion, there are some coastal state indicators that need to be specified. Many of them are terrestrial, so we need to know the dune strength, the coastline, the shoreline position, backshore, the dune, and the beach. But we also need to know the basal foundation, the sediment volume, which is underwater, so we need to have a cross-shore bathymetric profile, the surface volume, and the coastal slope. This is just an indicator of what we need to estimate the vulnerability of a beach. In other words, we need the coast, the beach in 3D. You have already said, the previous presenters, that we have done most terrestrial parts, and what is missing until now is the bathymetric part. So the beach system is actually, only a part of it is actually the subaerial beach. As you see here are some indicative numbers. The subaerial beach is for 50 to 100 meters, while the underwater part is some kilometers, depending on the slope of the beach. So what we have to specify is the wave breaking zone, which is very important for the sediment transport dynamics, and the nearshore zone, where the wave interacts with the seabed, and so we still have sediment transportation. And why the wave interacts with the seabed up to deep waters? Because the wave produces oscillations on the water column, which fade away until a point. This point that this interaction between the waves and the seabed is specified to around the half of the wavelength of the incoming waves. This can be specified. To give you a clue about how important the underwater topography is to erosion, coastal erosion, is that during summer, this is a typical profile of a beach system. This is the terrestrial part, this is the underwater. You can see that a big volume of sand is gathered on the terrestrial part of the beach. And there is also a sandbar here, which is a very important underwater feature. And it's created where the waves are breaking. You can see wherever a wave is breaking, a sandbar will be developed underwater. Now let's compare how the beach profile, the equilibrium, the so-called equilibrium beach profile will be formed during the winter. The yellow is the summer and the orange is the winter. You can see that during winter, where the waves are more destructive, the sand is moved from the beach, from the terrestrial part of the beach to the deeper part. This sand is not lost. It's just deposited deeper, and then in the summer it will go up again. This needs to be monitored in order to understand the coastal dynamics and predict the erosion that may happen. Apart from the cross-shore movements of sediments, there are also long-shore movements of sediments due to the long-shore drift, which is actually caused also by waves. Waves climb on the beach, then they retreat back, and so there is a composite movement parallel to the beach. This happens on the beach, so sediments are moving according to the mean direction of the waves, and this happens also underwater. So there is a big mass of volume of sediments moving along the shore. And this longshore drift causes a lot of well-known landforms like spits, tombolos, lagoons, some of them being very famous, like the Venice Lagoon or the Miami Beach or the New Zealand sand spits. So, according to the littoral shell, which is a coastal part that contains a complete cycle of sedimentation, including some sediment sources and sediment sinks, you can see that many parts are underwater. The deltas, the river deltas are underwater. They have to be mapped through bathymetric profiling and survey to see the extent of the deltas. You can also monitor the sandbars I was talking to you about previously. So you have to know where the sandbars are and how they move downwards and upwards. And you also have to know where the rips are, where sediments are lost down to the abyssal plane or the deeper parts of the ocean. Another thing that is very important, it has to be defined by bathymetric and sonar surveys, is the habitats, the underwater habitats. For instance, in the Mediterranean, we have Posidonia oceanica seaweed, which is very, very important because it stabilizes the beach, the underwater part of the beach, also the terrestrial through these dead leaves. But let's talk about the underwater. So it stabilizes the sediments in the shallow environments. So seagrasses and underwater habitats need to be mapped in order to specify the vulnerability of a beach system to erosion. Of course, there are other anthropogenic interventions that need to be mapped through and monitored through bathymetry, which are dredging or bypassing and some bathymetric changes that happen due to the installation of hard engineering works. Last but not least, we need bathymetry because if one wants to predict how erosion is going to happen in the future, he needs to do modeling, mathematical modeling. A model needs the atmospheric forcings that we have already gathered them through the monitoring stations that Professor Depudis showed you. But we also need to specify the coastlines and the bathymetry. So as you see here, we have to specify a grid with the coastlines, which are the red boxes here, where is the sea, and which is the bathymetry of the sea, the profile. So we need bathymetry, precise bathymetry, to conduct mathematical modeling also, as Professor Dimas will show you later. So, as you understand, it was very important to do the bathymetric survey in the Gulf of Patras. How we did that? We used a research vessel between a small research vessel, like one you see here, between 24th and 30th of September 2019. We used an ITER SWAT Plus multi-beam system, which is actually interferometric sonar. This one, we had a hemisphere GPS system, very precise, a motion sensor to detect all the movements of the ship and correct the beams coming, the bathymetric points coming from the multi-beam system, a navigation software, of course, and we also had an RTK GPS system to have very accurate positioning of the soundings. This is the cockpit, the interior of the vessel. You can see that we have installed all this equipment in the small vessel. Those are some data acquisition examples here. It is the ITER SWAT Plus system we used is a very accurate and very high precision system. You can have point clouds of some centimeters the one to the other. So you can have as high resolution as you want for the bathymetric mapping. As Professor Nikolakopoulos said, we also had a manned surface vehicle just for the very shallow parts where the research vessel couldn't go close. Through this, one can have bathymetry, bathymetric profiling, and even 3D reconstruction using the cameras on the vessel. So this is the survey planning in the Gulf of Patras. 52 survey lines have been conducted with a total length of 276 kilometers. The orientation of the lines was parallel to each other and parallel to the coast, and with a mean line spacing of 100 meters one to the other. The bathymetry was planned to be performed up to down to 20 meters depth. This was not random. We knew that the wave interacted with the seabed up to this limit. Now that we have data from the wave buoy in Patras, we can see that the mean period of the waves, the incoming waves, is 5 seconds, which can be translated to a mean wavelength of 40 meters. So the wavelength, the distance between consecutive waves is 40 meters. And so by the law of the half of the wavelength, which is the depth to the wave base, we can know that the wave interacts with the seabed up to 20 meters depth. So this is why we chose this extent. And here are some results. This is the general bathymetry. It has been exported with 5 meters resolution. It was very suitable for the mathematical modeling as an input for the mathematical modeling Professor Dimas will present you later. Here are some details. In general, the contours are smooth. We have some areas with rocky beds, but what is most impressive in the area is that it's very extensively covered by Posidonia oceanica meadows. So you can see here how high detailed the data are, the mathematic data are. We can monitor and detect all meadows through this complex texture that they create on the seabed. You can see how it is underwater, some photographs, and how it seems on the processed records of the multi-beam echo sounder. So, as a final slide, I'm showing you the extent of the Posidonia oceanica meadows, which, as said, are very important because they protect the shore from erosion, at least from big erosions. And so this is, the area is fully covered by Posidonia oceanica, especially the western part, except for the middle area, which is the Pyros River developing the delta. So thank you very much for your attention.
Okay, thank you, Ilias, for the very interesting presentation. Now, the next presentation, the title of the next presentation is Numerical Model of Coastal Erosion Processes in the Pilot Area of the Gulf of Patras. The presentation will be made by Professor Athanasios Dimas, Head of the Department of Civil Engineering, University of Patras. So, Professor Dimas, you have the floor.
Thank you very much. Excuse me, the title of my presentation, Numerical Model of Coastal Erosion Processes in the Pilot Area of the Gulf of Patras, work which was done by me and Dr. Yorios Lefteriotis. This is an outline of the talk, the introduction, the objectives of this work, a few words about the methodology, some typical results, and the conclusions we draw. the study area. This is to the left, you see here the Gulf of Patras. The pilot area is the southern coast of the part of Patras. And this part of the coastal zone is mainly affected by wind-generated waves from the northern sector of winds. The objective is to assess the coastal vulnerability in the pilot area of the Gulf of Patras using numerical simulations. In this particular study, we performed a couple of numerical simulations of wave propagation, wave-generated current, sediment transport, and bed morphodynamics using the tool by DHI Mike 21. We divided, to better study the area, we divided this region.
Ποια δίκτυα έβγαλε? Okay. We have a minor technical problem, so we are going to wait for a couple of minutes in order for make the necessary time to Professor Dimas to reconnect again. So I remind you, if you have any questions in order to be discussed at the end of the event, you can use the chat tool in front of your screen. So, concerning the rest of the program, after the speech of Professor Dimas, all the speeches and all presentations from the University of Patras are going to be concluded. And afterwards, we're going to pass to our next partner, which is the European Group of Territorial Cooperation, Evxenipoli. And this partner, Evxenipoli, is represented by the scientific team of Democritus University of Thrace. So, and I don't know if the control room. Okay. So we will try to reconnect to start again in the presentation with Dimas later on. Now we are moving, as I said before, to our partner from Evxenipoli, and the scientific team which represents this partner is the Democritus University of Thrace. The team is Professor George Sileos, Dr. Nikolaos Kokos, Konstantinos Zarchopoulos, who is a PhD candidate. All of them, they are coming from the Department of Environmental Engineering for the Democritus University of Thrace. The title of the speech, of the presentation, is Understanding the Patterns, Trends and Hotspots of Coastal Erosion and Climate Change Vulnerability along the coastline of Messolongi Municipality, blending modern geodatabases in a web GIS toolkit. So, Professor Sileos, you have the floor.
Thank you very much, Mr. Chairman. As we explained, we are not directly linked to this TRITON project. We are technical advisors to EGTC Evxenipoli, and we work mostly in the area of Messolongi municipality, as Messolongi is a partner of EGTC Evxenipoli. As I explained yesterday in the training days, coastal erosion is not only a natural phenomenon which has been enhanced by an anthropogenic influence, but there is also a process with significant socioeconomic impacts. As you can see, we have when we have an eroded area, we are losing sand, but we are losing also land, and we are connecting this and interrelate this type of damages to the ecological impacts. We are losing valuable coastal habitats, but we also create a series of societal problems. Coastal erosion is the combined effect of natural processes. From one hand, we have the impact of waves, tides, the impact of nearshore currents. We have to study very carefully the effect of storm surges and the imminent sea level rise, as we expect to have it as a continuously increased impact over the century. On the other hand, we have the human interventions like the urbanization, tourism, reclamation works, the coastal infrastructures, dredging, vegetation removal, the wakes created by ships, which again, in many cases are responsible for issues related to coastal erosion, the overexploitation of coastal aquifers, damming of rivers and torrents, and the excavation of sands and pebble deposits, especially in the rivers. All these are human interventions which create areas of significant coastal erosions. So if we look at the Mediterranean, and it's really a pity the fact that this map was created in 2004, and since then we haven't really a study which studied to study in a microscopic sense the coastal erosion over the Mediterranean. So this study from Project Erosion in 2004 explains that in the Mediterranean we have 1 out of 5 coastlines being eroded with a rate of 0.5 to 2 meters per year. So we see that coastal erosion threatens the highly ecological value land of 47.5 square kilometers. And presently, only 5% of the Mediterranean coastline are being protected by, mostly by hard engineering structures. Soft engineering is not yet a solution for most of the areas. If we see the issues related to what we will expect to happen over this century, we will see that sea level rise is gradually becoming a threat for the coastal communities. And we see here a map which explains that sea level rise due to climate change is not spatially evenly distributed. So you see that in the areas where we have these red colors, we have highest rates of sea level rise, up to 6.6 to 7 millimeters per year over the latest decades, while in the blue colors we have even negative rates of sea level rise. So this proves that the Eastern Mediterranean is, due to the higher temperatures that we expect and the warmer waters we are monitoring over the century, we expect to have the highest impact of sea level rise in the Mediterranean Sea. This is extremely important, and we should consider it in our future studies. So let's speak a bit about Greece. Greece is the country with the highest coastline length in EU. See, it has a length of 14,000 kilometers. And not only that, it has a GDP which has been produced by the coastal zone of the order of 114 billion euros. This is nearly half of the GDP of Greece. And this is produced over the coastal environment, the coastal zone. And we have a population living in a distance of 50 kilometers, which is estimated more or less 90% of the population of Greece. 10.1 million people are living in this distance. Yet, almost 30% of the coasts, around 4,000 kilometers, are eroding or appear to be vulnerable to coastal erosion. And this means that we need to define a clear strategy for the future. Greece, although is the country with the highest coastline length in the EU, for the moment it hasn't a clear strategy on what to do with these issues in coastal erosion. So why do we have these coastal erosion issues? We have them because we have damped most of our rivers and torrents, because we have stopped the supply of sediments to the coast, and we have built most of our coastlines, and this intends coastal development is really another problem, another factor which contributes to coastal erosion. With respect to climate change, there are various scenarios and studies that have been made over the years in order to study the different impacts and examine the impacts of the possible scenarios. And you see that if we have a sea level rise of the order of 1.8 millimeters per year, then almost half of the Aegean coastlines will be considered as moderately vulnerable, and the remaining parts will be considered as highly vulnerable. For the case of a sea level rise of 3.5 millimeters per year, then all of the Hellenic Aegean Sea will be considered as highly vulnerable to coastal erosion. This is the area of Eastern Macedonia and Thrace where most of our studies are taking place, and you see that following a series of satellite images, it's very easy for us to identify hotspots of coastal erosions. You see in the deltaic zone of Nestos River, after the damming of Nestos River in 1990s, we see significant loss of land as a result of this change in the balance and in the budget of sediments. Another area which is directly exposed to the southern winds and waves of the coastal zone of East Macedonia and Thrace is located here, the coastal zone of Rhodope. And we have in Alexandroupolis port, we have significant issues as the sediments which are being supplied by Evros River are blocked by the expanded port of Alexandroupolis. So we see here that there is an area of deposition as a result of this port expansion to the east of Alexandroupolis Gulf, and then all the rest is eroded as a result of this blockage. So in order to explain what is the scope of our study, we want really to improve our understanding of the coastal erosion using Earth observing systems and to define a clear methodology on how to design better protection measures in order to prevent the coastline, especially from extreme events, as we expect that over the century we'll have a higher frequency and intensity of extreme events. Moving to the study area of TRITON project, I would like to say that, as I explained earlier, it's Messaloniki coastline. It's a shoreline which starts from the deltaic zone of Acheloos River until over here to the west, and until the confluence to the sea of Evinos River. And within this is a zone of 45 kilometers approximately, and we have a complex, the major complex of lagoonal systems of Greece. It's a series of very important lagoons that produce fishery production, and it's very important for the local economy. So why we have coastal erosions and what are the main drivers of these processes over this coastal zone? We see that we have the wave action coming in the Patraikos Gulf, mostly from west and southwestern directions. We have nearshore currents, as you can see here. These currents are transferring sand from the west to the east. We have the changes in the SPM outflux from the rivers, and we have a series of exchanges between the lagoons and the coastal environment. All these are affecting the hydrodynamics, the wave dynamics, and the morphodynamics of the area. So now what we did, we used satellite images and we studied the evolution of the shoreline. We used different resources. We can go back in time, as you can see, back in 1985 until 2009 using Landsat satellite images from Landsat 4 and 5. But we can also use more modern satellite sensors like Rabbit Eye, which starts from 2009 to 2015 with a spatial resolution of 5 meters, or only for 2018, the spatial resolution of 3.1 when we use the data from PlanetScope. We selected a series of satellite images based on a series of criteria like the clarity from cloud cover, the correct georeference of these images, the seasonality. All images have to be retrieved in the summer months in order to avoid the influence of winter storm events, and the tidal effect. All images were retrieved in NIP tidals. neap tides. So based on this, you can see here the studied satellite images. We have developed a semi-automatic classification plugin system, which takes the images from the QGIS, the web, the GIS system that we use, which is a free and open toolkit. And we are using the near-infrared band from over here. You see this near-infrared image. And then we train the image. We have a neural network algorithm where we train the algorithm in order to understand which pixels refer to land and which pixels refer to the sea. We use this training in order to be able to identify the shoreline in a more objective way. And from there, we transfer the data from raster to vector, the image from raster to vector, and we extract the shoreline, which looks like this, and then we use another algorithm to smooth it. And this is a process which is now automatized in the lab. And then we have a series of satellite images, and we use a toolkit which has been developed by USGS and is capable to work in a GIS environment, and it's called DSAS, the Digital Shoreline Analysis System. We have we import the various images to DSAS, and then we use transects every 20 meters. Very high resolution analysis in our work in order to produce a series of coastal erosion statistics like the ones you see here, the node shoreline movement, the endpoint rate, etc. So these are statistical analysis that we do, and then we have developed a Python script in order to group our data and our transects into clusters that define areas of high or medium or coastal erosion or even accretion. So based on that, we receive tables like this with descriptive statistics on the quantitative analysis we do on satellite images. Now I move to the results. You see here what the situation is in the area of Mesologi coastline. You see that we have identified an area here of Louros Beach with moderate erosion. In Louronisides, we have high erosion. I will speak a bit later on that. In Tourlida Alikes, we have again moderate to high erosion, and there is a zone with very high erosion rates in Evinos deltaic zone. This is what we have seen from 1985 to 2009, and most of the issues we have identified in these periods have prevailed also in the next period from 2009 to 2019. This means that coastal erosion is enhanced over this period. We also try to identify the main mechanisms which are responsible for coastal erosion, and we use the Copernicus Marine Environmental Database, the Siemens Wave Database. We retrieved all data starting from 2006 until 2018. For these data points, you know that Copernicus has a grid of 4.5 by 4.5 kilometers, and we wanted to really utilize all this knowledge in order to combine the results of satellite analysis with the impacts of waves. So now moving to specific parts of the Mesologi coastline, you see here that in the Louros Beach, which is the westernmost part of the Mesologi shoreline coastline, you see that from until 2009, we have a mean shoreline retreat of 0.2 meters per year. This is an area where we have coastal erosion in the western part and accretion in the eastern coastal part. So more or less, this Louros Beach is part of a segment of the coastline which is in, let's say, a balance. So we have a redistribution of sediment along the coastal zone. In the western part, we have a retreat from 2009 until 2019, up to 0.5 meters per year, and a deposition of 0.9 meters per year. And this means that we have a longshore transport due to waves which are incident from southwest. You can see it over here. This is the direction of the waves as they come from the Copernicus database. And you see in the trends that this part of the coastline has more or less a steady condition. There is a mild slope over this model, and this is the equation which describes the retreat of the coastline, the change in the shoreline as a function of time. You see here again the distribution of sediments over this segment. In Luronisides, which is significant parts of the inlet of Mesologi Lagoon, we have three Luronisides, three small islands, Panistos, Kinias, and Koma. You see that we have waves coming again from west, southwest to northwest direction. But here the trends show that we have a steeper slope. We have highest erosion rates as we move in time. And you see that the red color prevails. So there is some kind of redistribution from west to the east, but we can say that we are losing sediment, and this is very clear. So we have to be very careful for Mesologi Lagoon and its capacity really to produce fisheries in the future, as we will lose the islands which formulate the inlet of the lagoon. In Alikes and Babakoulia zone, which is relocated to the eastern part of Mesologi Lagoon, we have for a period of time, until 2009, we had a deposition rate, a mean deposition rate of 1.2 meters per year. Overall, we see sediment accumulation in a canal called Babakoulia Canal. In the southeastern part of Babakoulia Canal, after 2009 until presently, we had a retreat of 14 meters per year. And overall, you see that the trends again show a moderate erosion, as you can see. And if someone follows this equation, he can extrapolate in time and see how the morphodynamics will evolve in the area. You see that we have a significant hotspot of coastal erosion as a result of the southern southern west waves propagating in the area. Finally, in the deltaic zone of Evinos, this is the major hotspot of coastal erosion. We have seen the huge sediment loss and land retreats up to 125 meters. This is an area that you can see it's a very steep slope over the years, and we are afraid that we will lose most of this zone as a result of coastal erosion if preventive measures are not taken. We think that we have proceeded by doing an extreme wave analysis for each grid point of Copernicus data, and you see here the various thresholds we used for this analysis. The maximum wave heights, you see that maximum wave heights are really high when we move from west to the east. This is because the western coastline is more affected than the eastern, and there is a longshore sediment transport from west to east. We have applied a very simple one-dimensional ray wave model, which takes the characteristics of the waves in the offshore zone and transfers them to the nearshore zone in order to calculate some characteristics of the waves in the coastal and the breaker zone. Mostly, we wanted to see the longshore wave-induced current, the direction and the magnitude, but also the incident wave energy in the breaker and the longshore sediment transport on an annual basis. So we correlated the outputs we had from the satellite analysis with the outputs we had from this very simple model by, again, which model has been forced by Copernicus Marine Environmental Service data. And we have seen that results show that the most energetic period was from 2012 to 2015. The mean wave energy incident on the coast was of the order of 80 joules per meter of coast width per second. This incident wave energy is increased and directly linked to the increase in the mean erosion rates over the coast, and in the longshore transport is favored, transporting sand from the west to the east. The highest incident wave energy was found in Louros Beach and in Prokop and Stos Beach, correlated to erosion rates of about minus 1.8 meters per year. Now, we also retrieved data from the climate change scenarios. The most likely climate change scenario is RCM 4.5, and we developed a series of wind analysis, wind box plots. We were interested mostly in the extreme events, the frequency and intensity of storms. As you can see here, over the latest decades of this century, we will have increased frequency and intensity of storms, which has to be again considered. We collected a series of data from various geodatabases available. For example, the bathymetry from JEPCO, the seabed slope. We have our own algorithm, but we used also the data from JEPCO, the river fluxes from EHIPE, the land uses from CORIN, the surface currents from Copernicus, and the SPM distribution, again based on Copernicus data and Sentinel data sets. And we have developed a WebGIS toolkit. We explained and we trained administrators yesterday during the training days. This is the WebGIS toolkit for the municipality of Missolonghi, and you see these are an image that someone can take related to the land uses. You see here that any user can see the direction and the strength and the magnitude of the winds and take data from the nearest meteorological station online and in real time, and also forecasted data. We have also digitized all the shorelines, and these are also part of this as a layer in this WebGIS toolkit. So you see here a very dynamic area with significant morphodynamics. And the user can also assess and see the coastal erosion hotspots. I believe it's a very interesting toolkit. You can access it from this website, and you can see, and of course you can provide us your feedback in order to improve. As a conclusion, I would say that municipality Missolonghi has a coastline which is exposed to the intense coastal erosion phenomena, especially in the area of Louronisides and Evinos. Evinos River discharge has been reduced over the year as a result of river damming, and this created a significant reduction in the SPM outflux, which again affected the coastal erosion processes on the area. Extreme weather events enhance coastal erosion processes. According to our climate change analysis, these extreme events will increase in frequency and intensity, especially at the western coastlines of the area, and the Louronisides will be the most vulnerable. We propose to clean the canals, transporting sediments to lagoons from accumulated sand, and use this sand to nourish Louronisides, because it's the most fragile ecosystem over there, thus reducing costs and efforts of this beach restoration. Thank you for your attention, and enjoy Greece.
Okay, we are back. Sorry for this interruption. Let me go a little bit back so that we have some continuation. This is, as we said, this is the study area. Oh, sorry. Just a moment, please. Okay. We're okay now? Okay. That's my. Okay, so the study area is the Gulf of Patras, and particularly the southern coast of the Gulf, and which is mainly affected by wind-generated waves from the northern sector. Our objective is to assess the coastal vulnerability in this area by using coupled numerical simulations of wave propagation, wave-generated current, sediment transport, and bed morphodynamics using the Mike 21 tool of DHI. We subdivided this region into 8 coastal independent subregions. You can see there in this graph with boxes the 8 subregions. And on the table here, you can see the mean grain diameters of the sediment, which was provided to us by our colleagues in this project. The numerical simulations include 4 stages. First, we determined by wave generation and growth the dominant waves with 1 year return period in the deep waters of the Gulf. And then for each subregion, we perform detailed numerical simulations for wave propagation and transformation, sediment transport and wave-generated currents, and morphodynamics in each of these subregions for each of the wind cases. First of all, wave development in the Gulf of Patras, we used wind data from the Hellenic National Meteorological Service from the stations at Nafpaktos and Araxos. We determined the wind speed with 1 year return period and perform wave growth and development simulations in this area you see here, which includes not only the Gulf of Patras, but also the Ionian Sea west of the Gulf and the islands of Kefalonia and Zakynthos. The Mike tool uses a numerical solution of the wave action equation in order to produce wave generation and growth from wind data. This domain was discretized with approximately 180,000 triangular cells. Some typical results. Up left, you can see the wave height distribution from west winds, and you can see the mean direction of the generated waves. And on the right, the same picture for northeast winds. In the table below, you can see for each of the wind directions, which is the wave speed with 1 year return period, the wind intensity in terms of Beaufort scale, significant wave height, wave spectrum period, and the mean wave direction with respect to the north. So we have established the wave climate in this in the area of interest, in the deep waters of the areas of interest, and then we moved into performing numerical simulations for each of these detailed simulations for each of these areas, using the bathymetry which was provided to us by our colleagues in TRITON. And also for deeper water bathymetry, we used the CMAP database of the numerical tool. Here, for example, you see a typical result for subregion 1 for wave generated by northeast winds. Specifically, you see a distribution of the wave height in this area and wave celerity, which, as you see, is affected by wave diffraction close to the coast, as expected. For the same area, for the same wind, the results of the wave-generated currents, which are mostly longshore. You can see that in the eastern part here, you have currents, from east to west. But then there is a circulation, hydrodynamic circulation generated in the western part. You have close to the coast longshore from west to east. Plus, in this result, you can see the wave setup, which affects the inundation of the coast. And then, for the same area, the same wind, the prediction of coastal transport, the magnitude of the coastal transport, and the prediction for erosion deposition rate of change in meters per day, which gives you an indication about possible hotspots for erosion. Another typical results for the subregion number 6, you can see in the up right corner. For this case, we show the northwest, the waves generated by northwest winds. Again, wave height distribution and wave celerity in this area. Currents, here we have a dominant west to east direction in the longshore currents, and weaker coastal, weaker wave setup in this in the coast. Plus the distribution of sediment transport rate, and the prediction for the rate of bed level change in this area. Based on all these results, our main conclusion is that mostly northeastern and northwestern waves have the dominant impact in terms of erosion in the area, and specifically northeastern waves affect the entire coastal zone, apart from a small part of the eastern side of the area, but also the northwestern waves have an important impact, mostly on the eastern part of the area. Western and southwestern waves have a very weak effect in the area in terms of erosion. Based on that, we graded the effect of erosion from zero, I mean practically zero, to low, to moderate, to high, in order to assess the effect of each wind on each particular subregion, because this will help. We believe that this will help planners in order to design the best possible coastal protection works or methods to protect this area. Thank you very much, and sorry about this interruption before.
Thank you very much, Professor Dimas, for the very interesting presentation. Now we're moving to the next presentation. The title of the presentation is Evaluating Coastal Erosion Risks in the Ugento Shoreline, a machine learning approach supporting multi-scenario analysis. The presentation will be made by Dr. Elisa Furlan, representative of the Euro-Mediterranean Center for Climate Change, CMCC Foundations from Italy. So, Elisa, please welcome, and you may have the floor.
Thank you, Chairman. Thank you for the floor. Let me show you briefly the screen. Okay, good morning, everyone. I'm Elisa Furlan, and I'm a scientist at the Euro-Mediterranean Center for Climate Change. Within the TRITON project, we have been involved as leader of the work package 3, dealing with the mapping and planning of tools and framework for coastal erosion risk assessment and management. So dealing and leading our package, focusing on this topic, my talk today will focus on the evaluation, the development of a machine learning-based method for coastal erosion risk assessment and management. So I want to briefly summarize you the main contents of this presentation. Moving from our first preliminary explanation of the motivation objective behind our analysis and application, I will move on the theoretical background underpinning the design of our method. And then I will move on the case study, the data collection underpinning the Bayesian network approach, the machine learning-based model design and training. So finally, I will show you the resulting output from the application of the method to the TRITON pilot case of the Ugento shoreline located in the Apulia region. So it's widely recognized as climate change is leading to severe threats to coastal area, mainly due to the complex interplay among natural pressure, mainly related to rising sea level, changes in the dynamics, the energy distribution of waters, but also the variation in the pattern, frequency, intensity of extreme events that are highly affecting our coast. Alongside this natural pressure, we can find out also increasing anthropogenic pressures, mainly linked to the coastal development and the connected land use changes. As a consequence of this complex interplay, we can observe a rising cumulative impact and coastal erosion phenomenon along the Triton, but also, along Europe and all the coasts, but with the focus on the Triton pilot case, we can observe a high erosion rate with the cascading effect on water quality deterioration, biodiversity loss, and also damages and losses to ecosystem service flow. Against this complex background, our planners and policymakers are increasingly calling for new approaches and tools, allowing a sound evaluation of erosion, of coastal risk, but also allowing and supporting them in the definition of management measure and integrated approaches for the sustainable use and management of coastal area. So far, we observe the research community develop a different kind of methodological approach dealing with this topic and addressing, searching to face this kind of complex analysis, moving from simple indicator and index-based to more complex remote sensing techniques, as that previously presented by Professor Silaus, and also more complex machine learning-based methods, including Bayesian network approaches. But maybe what is a Bayesian network approach? So just in a nutshell, Bayesian network approaches are probabilistic graphical models that allow to represent the system components, so the different variables at stake in a complex system and their relationship in terms of conditional interdependency by combining the principle of graph theory and probability theory. We can say that the key added value of this kind of machine learning-based method is that they allow to consider in the same framework, in the same system, multiple stressor and assessment endpoints. So in this way, they allow to support the modeling and analysis of complex environmental systems such as marine and coastal environment. Moreover, they allow to integrate different knowledge domain, expertise, and data source. So we can integrate GIS data from numerical models, but also expert judgment and rules underpinning multi-criteria decision analysis and environmental indicators. So we can say that they can act as a decision support tool informing coastal risk assessment management. So this is why we decided to use this tool in the frame of the TRITON project. We explore the state of the art of this method, deeply analyzing the frame of the work package 3 together with our partner. The different Bayesian network approaches are already applied by the research community, that they move from simple model integrating only the driving variable related to the driving forces of shoreline change rate to more complex model that allow implementing the consideration of environmental and human receptor as assessment endpoint of the analysis, but also to analyze through the scenario analysis the potential effect induced by the management measure. Moving from this preliminary review, we can say we searched to develop and tailor a Bayesian network approach specifically designed for the TRITON pilot case of the Apulia region. That is the region in Italy characterized by the longer coast. We talk about the 917 kilometers of coastline, mostly flat and characterized by sandy beaches. And according to the regional coastal plan, we can recognize, as you can observe in the table below, that about 32% of the coast is retreating. So it's experiencing erosion processes. More specifically, in the frame of TRITON, we selected the municipality Ugento as a case study of our application, since it has been selected as the best practice for coastal erosion management, since the municipality so far implemented different kind of management measures to deal and face coastal erosion processes, especially putting more effort recently in the implementation of nature-based solutions. Moving from the case study area, in order to design and especially train the Bayesian network approach that as all machine learning based methods that are data driven require a lot of data to be trained, we collected a huge amount of data regarding mainly the oceanographic forcing, so the forcing of shoreline movement, but also data related to water quality parameters, because in our Bayesian network model, we searched to explore the nexus among coastal forcing, oceanographic forcing, and the effect of shoreline evolution also in terms of changes in the water quality, so changes in turbidity and the transparency of water. So all data were basically collected from the Copernicus Marine Service and were then pre-processed in order to be integrated in the network, in the BN model. As already presented by Professor Silaus, we also apply remote sensing techniques, so a semi-automatic automatic classification in order to identify, to extract the shoreline against the 2008 and 2018 timeframe. So in this way, we were able to identify 4 hotspot risk area, especially identify Torre Mozza, that is the southern part of the map, you can see, with the higher erosion rate, and Lido Marini with a balance among retreating and eroding coast. Once all the data has been processed, we can move to the design of the Bayesian network model. And just to summarize you, the main step underpinning the BN development, we can recognize as a first step the design of the conceptual model that basically allow to define the structure of the network, identify its main variables that are represented by using a conceptual influence nodes and arrow diagram. Then, once the model has been defined, we can move to the model parameterization, where we can define the states for all variables that can assume the form of interval, a Boolean classification, or a labeled according to expert judgment, for instance. And then, according to the parameterization, we can move to calculate the prior probability resulting from the data distribution, the real data distribution. Then, according to the linkages, so the connection on the variable, we can move to analyze the conditional probability, so the strength of relationship among the variable. Then the model can be calibrated and validated. And finally, once the model is validated, we can move to the scenario analysis. So we can infer the behavior of the variable at stake in the model against different conditions. So we can say that we can set an evidence, changes the prior probability, and then we propagate the evidence to the variable, the nodes that are connected in the network model, in the Bayesian network model. And then we can observe the changes in terms of posterior probability. So in this way, we talk about multi-scenario analysis. So going quickly on the implementation of the methodological steps. So for the BN model design, we started from our extensive review performing the frame of the work package 3 of TRITON, and starting from the conceptual framework already developed by the research community, we defined our model that is basically a deep sea framework, identify all the driver, the pressure, the changes in state, and the potential impact in our Ugento case study. From this conceptual framework covering, that we can say that is general and cover all the different variables, all the different forces that can be considered at the case study level. Then we also took into account the data constraint. And then we move to define our Bayesian network model that, as you can see, this is a preliminary expert-based Bayesian network model, which has been classified according to 3 main groups of variables, namely oceanographic driver, with the highlighted in the light blue balloon, with the management measure with the green color, and the assessment endpoints with the red color related to the SPM, that is a suspended particulate matter, the KD, which relate to the diffuse attenuation, and the SEV related to the physical shoreline movement. So we also explore through the application of constraint-based algorithm, but also score-based algorithm. We learned the model in order to explore for new potential linkages resulting for the analysis of the conditional probability among the different nodes included in the network. And according to this automatic model learning, we observe a new linkages among the variables related to the wave and the wind height. And so we finally we defined a new arrow connected to variable. Finally, once the model has been defined, we parameterized our model, classifying our variable, especially for the oceanographic drivers, we discretize the ranging value into 3 or 5 equal interval classes. For the management measure, we identify Boolean values. And finally, for the assessment endpoint, we manually classify into 5 classes in order to better visualize and discretize the resulting output from the scenario analysis. We also validated our model. Let me go behind. And we observed that by applying the k-fold cross-validation, we observe a mean prediction error of about 30%, we can say. Prediction error that is higher for the shoreline evolution, mainly related to the data input, we can say. And a prediction error that is reduced under the water quality parameters with about the 27% for the KD, that is the diffuse attenuation. So going to the scenario analysis, once the network is validated, we can move to the scenario analysis. And in the case study of the Ugento shoreline, we analyze 2 different scenarios. The first one that we call a rapid changing world, when we envision the possibility of a higher significant wave height as a consequence of a change in the climate pattern. So we can say that we figure out a rising in extreme events. And then the second scenario, focusing on the implementation of a new natural-based solution along the coastline. So basically exploring what are the required management measures to face coastal erosion risk in the area. So, looking at the resulting output from the scenario analysis, when focusing on the scenario 1, the rapid changing world related to the extreme events, the rising extreme events, with a higher probability in the highest state of significant wave height, we can observe for the shoreline evolution parameter assessment endpoint an increase in the class. So as you can see in the image, in the bar chart, with the dark green and the red color, we can see an increase in higher correlation and higher erosion. So we can say that the most dynamic shoreline, status of shoreline increase. But if we implement new management measure, new natural basis solution along the coast, such as those already implemented in the recent year by the municipality, we can observe basically a reduction of the coastal of the state of the shoreline in higher erosion state and also in higher accretion. So we can say that the mostly dynamic cost decrease, increasing the percentage of the moderate accretion state and moderate erosion state. Moving to the water quality parameters, in this case, under a rapid changes world, so with the higher extreme events, we can observe an increase of the high and very high classes, mainly related to the movement of the suspended matter on the left and on the right for the diffuse attenuation that is related to the light through the water. And when we move to the green is the new black with the implementation of natural basis solution, we can see, I mean, also in a minor extent, a reduction of the impact as we observe for the shoreline evolution. For the water quality assessment endpoint, in both scenarios, the rate change is less significant compared to that we observe for the shoreline evolution. Maybe also in this case can be related to the data input that we use for the analysis, but also to the possibility to link the water quality changes to other kind of variable, such as the precipitation, new variable that will be implemented in a new and advanced Bayesian network model. So building on this last sentence, we can say that to conclude, the Bayesian network model that we develop is a replicable and easy to use tool that can allow to take into account the complexity and uncertainty of the coastal system, because it allows to also embrace a broader concept of coastal erosion link, exploring the nexus between the oceanographic boundary condition, but also the management measure and their effect in terms of changes and limiting coastal erosion processes and changes in the water quality. And in this way, it acts as a decision support system to drive effective integrated coastal management, but also adaptation planning in the perspective of changing climate pattern. It's a flexible tool for interdisciplinary studies, and we can, as I told you, update the model continuously by integrating data with higher spatial resolution, because in this way we use Copernicus data with a core spatial resolution, but it was the best data available for the case study. We can say that we can find out also limitation in this tool, mainly related to the input data, but also the limitation of Bayesian network in modeling complex synergies and temporal changes. So for instance, cascading effect in different sectors and according to different time duration in the perturbation. Also, the parameterization of the variable, as I showed in the previous slide, allow for a poor representation of the past spatial temporal dynamic of complex environmental processes. And also, another gap is the output that so far is only we can say a bar chart representation, a probability distribution that needs to be also represented in terms of a map. So we need to move from a GIS. We need to move to better integrate GIS and BN in a mutual dialogue. So future development of our work for sure will include the analysis of dynamic pattern of the coastal environment by implementing more complex and advanced machine learning based methods such as recurrent neural network, convolutional neural network, in order to better capture this spatial temporal dynamics in the erosion processes. And we are sure that in the way we will be able to pave the way for the implementation of this new, more complex machine learning based method, we will be able to provide useful support and useful tool for integrated water resource assessment and management in the frame of a wider and comprehensive integrated coastal management. Thank you so much, and thank you for your attention. Thank you.
morning. Good morning to everybody. Can you hear me?
Yes, Michela, we can hear you very clearly. Now we're moving to the next presentation, the 7 key performance indicators toward an effective coastal erosion prevention and integrated maritime spatial planning in EU SER. The presentation will be made by Michela Cariglia, a blue economy expert, representing our leader, which is the Apulia region. Michela, you have the floor.
Thank you very much. Thank you to everybody. And last but not the least, my presentation will be very, very fast and give you an overview about the main results of the project that become key performance indicators that will achieve the objective of replicability and transferability of the methodology and results of TRITON project at EUSER level, but it's I have an update to all of us because with the cooperation with the CMCC, the best practice of Ugento that has been carried out within the work package number 4 become best practice at European level in cooperation with the environmental agency, with the Agency for Environmental of the European Union, and it's a great results in terms of spreading of the methodology and the work that we have done within TRITON project. So the presentation will give you an overview about TRITON at a glance, because starting from the input of the project, we outline the performance indicator that should be used for integrated management and maritime spatial planning in the perspective of cooperation, because the coastline are not only part of the state and the region, but they belong also to the entire community. And so at the beginning, TRITON has got an innovative approach, and this approach gives us the results that can be combined among themselves, can give the added value that is required from this kind of project. So all the items will be part of the platform as repository data, but also with the double link with other project and methodology, because it becomes part of the decision supporting system that we call coastal supporting decision system. That is a specific tool that can be used from the different stakeholders. What I would like to highlight is that we should consider, and the lesson learned from TRITON is to consider the integrated coastal zone management and maritime spatial planning as an opportunity, as much more than an opportunity, and the results is related to the fact that we start to indicate a methodology to create the integration of different stakeholders. That is one of the key performance indicators that we are going to highlight, and it was very useful during the project. The project development, because we have a real effective measurement about, first of all, the awareness, and second, the methodology and the real effect of the action that we are going to put on the table. The 7 key performance indicators that have been outlined within TRITON project are related for give an overview and instrument for advancing coastal risk management, and they are provide actionable information, prepare and empower information use, created decision support products and service that turn scientific advances for societal benefit, build strong partnership, develop the next generation workforce, align roles and responsibility, and recognize linkages and potential leverage. And those indicators were not considered as input in TRITON at the beginning, but they become from the integration of the different work packages. As you know, to provide actionable information, we should merge different indicators and different implications. What coming out from TRITON is that the natural and social sciences should work together, because the socio-economical implication need to be considered not only in the management of the damages, but science the planning and the risk management. And those information should be integrated and should work together. And to do this, we need to give to the different operators this coastal decision supporting system. In TRITON, despite the fact that the project is a standard project with a low dimension, but gives the opportunity to check all the parts that can become or not become, taking into consideration that we are working in a not so small area, but with very defined stakeholder, is we try to give the information and to create a template that can be used in EUSER perspective to develop the coastal decision supporting system as part of the planning for local communities, regional communities, and international community. And now we demonstrate how the interaction of data must be processed with forecast and predictability as far as concerns the intervention, and taking into account economical aspect and social approach. What we did is to add and to consider the economic value and the economic valuation according to the Marine Strategy Framework and the protocol on integrated coastal zone management. And with the pilot case, we try to check what is going to happen given a value on the coastal management as indicator. The value is based on real cost of each intervention, so not an estimation cost of intervention in terms of prevention, but also in terms of planning and reduction of risks in the predictability dimension, and also to identify the financial instruments to follow up with the planned intervention. The second key indicator is the awareness about the importance of empower the information users, because one of the lack that we assume during the project preparation and even in the project development was the necessity to overcome this bottleneck, because there are a lot of information not aggregated and not immediately available at the different levels. And so the stakeholders, but also the emerging managers and the other practitioners and policymakers and the media and the community that depend from coastal management need to be ready to use the information. And this is a sort of not only an understanding but also an engagement of effectiveness. And in TRITON, we propose the solution to achieve this indicator in the paradigm learning, testing, training. Learning, testing, training is to understand and to learn how to use the different available tools. In the platform, we will see that we don't have only the link and the repository, but we also demonstrate how we can match and how it can become a it's a practical tool for the different level of the users involved in the procession of maritime special planning and coastal management toward the prevention of the risks. And so learning to use the different tool, test on the specific area is what we did in Greece and in Apulia region, and training from the different lessons. And the training session that were part of the project become a methodology that can be applied and have got also an effect on the project duration, because it's in continuous evolvement and give the possibility to perform different level of approach. And it was interesting to see the interaction, because the table that we published within the work package number 3 was created during the training session carried out in Italy, and it has got a real bottom-up approach into the dimension, and it's a sort of methodology that can be used in the engagement of the users toward the preparation and empowerment of the information as tool and as something available, having the attention with other possibility or other success case carried out. What we did is the creation of the interaction of elements on the Italian side, GIS and web GIS that were available at regional level together with the legislative framework. But what we did is to create a table of content and an index that give the possibility to capitalize the existing results. So we start from a demand and we propose a solution. And this is the workflow of interaction to empower the information user. As you can see, we have different stakeholders and we have different demand. What we did is to create this knowledge hub, starting from the maritime special planning, integrated the ICZM and the results of the project with the pilot cases, and creating a catalog toward the risk prevention. Third key performance indicator is the integration of services and decision supporting system for using the scientific advances and the awareness and increase of awareness in social benefit. And so within the pilot cases, we have scenario-based exercises that help to identify avoidable risks and recommend response option. And a lot of these indicators become part of the perception and of the community, but also of the municipalities, in order to allow and to increase the awareness related the integration of risk management into the decision making. The solution that TRITON proposed is to enhance the coastal decision supporting system as performing tool that give the possibility to be checked and to be consulted in several situations, but with the clear link to typical situations that are already afforded in other areas. The fourth key performance indicator is related to the necessity of create strong partnership among the different stakeholders, information providers, information users, and the stakeholders. That in the coastal management, we are aware that staking different approach, and we are aware about the fact that to afford and to manage the water resource, we have to respect the different views, but also to identify the shared values. And in the pilot case, both in Greece and in Italy, we achieved this objective, and so the TRITON solution to overcome the lack in coordination of partnership and the lack in coordination of information users, providers, and stakeholders could be achieved in the evaluation of problem to solve, current situation, and possible solution. The possible solutions are described in several experiences, and it's just enough to have an overview using the instruments that are available, like the one provided by TRITON from YELS from United Nations, and the experience carried out in other projects that can be applied at user level. Taking into account that the coastal erosion risks and prevention is not only a pillar of the blue growth, but it's also an exigence of the EUSER region, and should be taken into account, because the coastline are similar, and the problem and the lacks are similar in the different countries involved. And we select from the indicator five steps that should be used to have the creation of this strong partnership, and they are the establishment of informal transboundary working group. We did within this project with the involvement of different stakeholders, but and it's one of the output of the project, the memorandum of understanding, and the working group using the platform can share input and data. Use the propose for cross-border or transboundary area to be planned, and so identify the program preparation, the possible areas of intervention and the potential partner, the definition of common planning and management goals. And the data alignment and sharing is part of the data management. The speeches before mine went very deep in this point. And it's also important to create an indicator or a pattern of instruments for analyze and assess the human activities and their impact at transboundary level. So we take into account the frame created in the Baltic Sea area that can be used at EUSER, and it's the creation and the building of a Pan-Adriatic Ionian Maritime Special Planning, considering into the Maritime Special Planning also the integrated coastal zone management and also the coastal erosion risk prevention as part of the maritime special planning. And for instance, the West Med initiative founded by the European Union is going to follow this kind of approach. And so we can do the same using the best practice of the Baltic Sea that is similar to EUSER. And it's important to stimulate the dialogue also with the different stakeholders, even out of projects. And here we give you some outline and to take into account how the integration and the process of creation of a strong partnership should be something that starts from mutual information to common strategic plan and implementation of the strategic plan. And in this sense, TRITON is an opportunity, is a great opportunity to be capitalized for the program in 2020-2027. The fifth point, the fifth key performance indicator is related to the need to develop the next generation workforce. What it happens within the COVID give us a great lessons, and what happens within TRITON also give a great lesson about this need. And the next generation workforce should combine the public's well-developed capacity to the use of information and to the power of the use of existing tool. And the TRITON solution we present with the work package, when we carried out with the work package number 5 related to the training, give the starting point of this kind of approach, that and give also the opportunity to create job places, and the training part demonstrated that the efficiency of an area based integration for coastal management and risk of erosion prevention should be integrated with elements like the adoption of more area-based approach instead of sectoral. This one was one of the lack of awareness into the trainees, especially when we are going to plan the marine space. We should take into account the workforce that has to be ready to choose the right limits and scales of the marine management units and the limitation. Ensure the respect of marine ecosystem and waters with the management units that can be considered also as business unit. And the designation of MPAs, the expansion of existing network, because an engineer can, for instance, an infrastructure engineer can have and should have an approach with those criteria for perform not only the next generation workforce, but even the optimization of the current workforce. The sixth key performance indicator is the need of aligned roles and responsibility, and those indicators include a setting of standards. First of all, the identification of best practice Second, the providing of a repository case study and lesson learned, and it's what we did within TRITON, help to ensure and enhance the public goods as something that belongs to everybody, and to identify, since the project preparation and the program preparation, the resource to support the efforts at local and regional level, and how those resources are applied to the different local communities, and how they can be widespread with adoption and success into the application. The TRITON solution identify in the analysis of the indicator effectiveness the criteria of putting a price on the coastal ecosystem. If we put the price on the value of the interaction of different users and stakeholders and the alignment of this, we can have an estimation of, in terms countable, of the importance of the coastal ecosystem and the maritime special planning and the risk prevention as a way to align the roles and the responsibility. And it means the integration of, for instance, coastal tourism and aquaculture and the different voice of the blue economy. If we put a price for each community to the different voice that belong to the different voice of the coastal ecosystem, it's possible to have this indicator and to use it in the roles and responsibility and the sharing of the different roles and responsibility. It means that we should approach the coastal management and the maritime special planning as accountable coastal erosion management, and we outline how to achieve this objective with 8 points. And during one of the bottlenecks exercise carried out during the training session, the trainees developed this kind of approach, and they change their opinion and consideration also into the financing program. The seventh key performance indicator is something that seems to be clear, but it's not so often applied. Is the recognition of linkages and potential leverage. And the coastal risk management project at Italy-Greece level, but also in the OSER perspective, need to be are characterized to the aiming of achieving multiple goals, but very often they don't have a lot of appeal in the local communities, and they take into account as main goal the economical impact and social impact, and they don't take into account enough the environmental impact. In the case of the recognition of linkages and potential leverage, it's possible to identify common needs, case studies, and lessons learned, and to link themselves using the coastal decision supporting system. This workflow gives an overview about the importance and the importance of this indicator, this key performance indicator, and we have the sample with mentioning what happens with Finland. And in the experience that we carry out with Finland, despite to the consideration of social, economic, and environmental aspect, they take into account also the social impact in the perception of the local communities to have the same landscape in comparison. The case was related to Ugento Dunas that was exploited by Elisa before. And what is going to happen if we are going to replace the sand and the dunas has got the same landscape, and what do the people can think about the different approach? And we solved this integrated tree system. The pictures, of course, and the GIS system, and the double check of the situation ex ante and ex post, and the message that has been sent to the community. And if somebody would say that it's quite possible to merge Puglia region with Finland, I would say no. Instead, with the linkages and the leverage, we assume now we can declare that it's possible to create this kind of linkages. The TRITON solution adopt as main pillar the concept of resilience. Resilience and the coastal resilience should be taken into consideration for similar areas with the proper assessment and according to the Bayesian model as well as described within TRITON project. It's important to have a better understanding of neighboring, a rich common conceptualization of planning issues and goals, and closely cooperated in gathering the exchange data and relevant information. How those KPI will live from TRITON to the user. And I would like to use these comics that give exactly the perspective of what we can do and what it's possible to do. From a problem to a solution. Where we are in the position that we define using the different system studied within this project. We are in the position to have a definitive simple tool, and we have 7 indicators that can be used for all the area. For all the area, and can give the perspective of the project spread out of results and methodology even beyond the project duration, and they can become a methodology, and they can set up the rules for the next programming period. And I would like to finish my speech with this other comic that show the ecosystem and the ecosystem. And we have the possibility with the spreading of TRITON results to create an ecosystem for the user and beyond. Thank you for your kind attention, and I really hope to meet you soon and to apply what we identified. Thank you.
Thank you, Michela, for the very interesting presentation. Now we are moving to a very interesting video presentation from our Italian friend. She's presenting the coastal planning in Bari. And afterwards, we're passing to the final part of this event, which is questions and discussions. So please, if you are ready, see the presentation of the video.
waterfront di San Girolamo e Fesca è un intervento che ha avuto uno sviluppo in lunghezza di circa 1,7 km, ha completamente riqualificato e cambiato in meglio la vita e gli spazi pubblici di due quartieri importanti, appunto gli omonimi quartieri San Girolamo e Fesca. È un intervento che si colloca all'interno di una strategia ben più ampia messa in campo dall'amministrazione comunale, una strategia che punta a riqualificare completamente i 42 km di costa che vanno da Torreammare a sud fino all'estremità più a nord di Santo Spirito. L'obiettivo è duplice, è quello di collegare fra di loro questi 42 km di costa, ma soprattutto di riqualificarli cercando di riscoprire un nuovo rapporto con il mare. Questo nuovo rapporto con il mare è stato letteralmente conseguito proprio nell'intervento di San Girolamo e Fesca, lì dove è stata spostata una funzione prima importante eseguita da quel tratto di costa, era una funzione trasportistica di collegamento di una strada che è stata arretrata nella parte più interna del quartiere, mentre sulla costa sono stati realizzati spazi che hanno l'ambizione di sviluppare la socializzazione fra le persone. Una pista ciclabile lunga 1,7 km, ampi camminamenti, moltissimi spazi verdi, spazi dove potersi sedere, abbiamo stimato oltre 6.000 posti a sedere, oltre 20.000 piantumazioni, di cui 200 alberature, rappresentano i numeri di questo intervento che ha letteralmente cambiato le abitudini di questo tratto di costa. Non solo, abbiamo conseguito anche uno sviluppo economico della zona, molte sono le attività commerciali che hanno trovato interesse in locali che esistevano, moltissime sono le attività edilizie di recupero di vecchi manufatti che erano abbandonati da anni, e poi ci sono gli interventi edilizi realizzati nell'ambito della Piazza sul Mare che, messi in concessione da qui a breve, permetteranno di avere la giusta vitalità sia per attività commerciali ma ancor di più per attività sportive che renderanno vivo tutto l'anno questo tratto di costa. I prossimi interventi che la città ha calendarizzato sulla costa sono il rifacimento del lungomare di fronte al tratto della città vecchia di Bari Vecchia, un tratto che verrà letteralmente riqualificato e che ingloberà anche il molo Sant'Antonio e San Nicola attraverso il Teatro Margherita. Poi abbiamo un'estensione dell'intervento che interessa il lungomare monumentale fino a Pane e Pomodoro a Torrequetta. C'è tutta la riqualificazione della costa sud che è stata oggetto di un concorso internazionale che arriva fino a San Girolamo. Abbiamo già una progettualità per sviluppare un tratto di costa di circa 2 km in Torreammare e abbiamo in corso di esecuzione, peraltro con lo studio di Boigas, proprio lo stesso di Barcellona, una riqualificazione dell'area portuale e costiera di Santo Spirito. Questa è la strategia che la città di Bari ha in atto e in programma per i prossimi anni. Lungo l'Adriatica c'è una pista ciclabile molto importante di valenza europea, è una pista che ha una criticità, una discontinuità proprio in terra di Bari, ed è una discontinuità in corrispondenza del canalone Balice, lì dove non è possibile percorrere e attraversare questo canale in bici, e quindi questo non permette di avere la continuità con i quartieri di Santo Spirito e Palese, ovviamente partendo da Bari città attraverso San Girolamo e Fesca. È una criticità che verrà risolta anche qui a breve. C'è una candidatura per un progetto di una passerella ciclopedonabile per la realizzazione anche di un ponte carrabile ovviamente urbano, che andranno quindi a integrare quelle funzioni trasportistiche oggi assolte esclusivamente dalla strada statale, che come tutti sanno è una strada extraurbana che però assolve anche alle funzioni di circonvallazione interna, facendo dialogare due quartieri importanti della città fra di loro, e questo crea grossi problemi soprattutto negli spostamenti. quest'estate, proprio all'indomani dell'inaugurazione, sono stati organizzati tutta una serie di eventi tra i più disparati, alle proiezioni cinematografiche, agli spettacoli artistici, alle competizioni sportive, a dimostrazione di come questi spazi presentano una forte vitalità, una forte versatilità nell'utilizzo e soprattutto un elevato gradimento, perché sono tutti interventi che hanno visto una grandissima partecipazione di persone.
So, with reference to the intervention to the west of Bari, called Promenade or Waterfront from Fesca to San Girolamo, the team of designers had to reach several goals: to protect a urban area from overtopping and storms attack, which was damaging every year at least 2-3 times the road, the path. So then to create new beaches for recreational use. In fact, that was an abandoned area with some buildings, people living there, but without recreational activities. And to create a small port for sport and pleasure boats. And then finally to interconnect the new buildings with the sea. So these goals have been achieved by the construction of new coastal structures, a square at the sea, the construction of pedestrians and bike paths. In addition, it was created a kind of dune, because originally along the coastline there was a dune. So an artificial dune has been created with vegetation typical for a dune. The erosion phenomena is related to the use of the coast, or what is going on along the coast. The erosion comes because no more sediment is reaching the beach, the coastline, because we have reservoirs along the rivers, we have no natural water coming to the river, to the sea, sorry. So this causes a lack of sediment. The protection, the coastal protection, is also a cause of a lack of sediment to the beaches. So erosion is related to the use of the land from the man. In fact, if you go to an area without human presence, then in that area the erosion is not existent. So we have to consider this. 20 million years ago, the sea level was 130 meters below the present sea level. So now we are so worried about the climate change impact on sea level rise. We expect 50 centimeters more at the end of this century. So why do we worry so much about this increase of the sea level? Because we have created an hard coastline. The coast has to be dynamic, so we cannot create hard structures along the coastline. The roads, the buildings have to be avoided along the coastline. Right now we have a lack of sediment, and we have to protect the remaining sediment or to nourish the beaches.
Okay, we are back. As I have checked, there are no questions to discuss from the presentations that have been made. So we can close today's final event. Just a few words from me. I would like to thank, first of all, our hosts, the region of Western Greece, the governor of the region, and the team, our partners in this project, for this successful and very efficient event. Also, I would like to thank our presenters, and to remind that all these presentations have been made from the partners of the TRITON project. So, thanks everybody. Thanks everybody for their attention. And all the event, as I have been informed, will be open as a YouTube link in the site of the region and the site of the TRITON project. Thank you very much and have a nice day.